Florida is racing into the future with mega projects so massive, they're transforming the state from coast to coast. From next-gen highways to billion-dollar towers rising over the shoreline, these builds are rewriting how Florida lives and grows. Let's reveal Florida's mega projects completing in 2025 and why the Sunshine State is now the most ambitious construction zone in America. Located in downtown St. Petersburg, Florida, 400 Central is a significant high-rise residential development that exemplifies modern urban engineering and construction in a coastal city environment. The project is designed as a mixed-use tower rising over 40 stories, integrating high-end residential units with retail and office space on the lower levels. Construction of such a tall structure in a region known for hurricane activity and a high water table requires sophisticated planning, extensive geotechnical assessments, and specialized foundation engineering. Prior to vertical construction, crews excavated and stabilized the site, installing deep foundation systems that likely included drilled shafts or auger cast piles extending dozens of feet below grade to reach competent load-bearing strata. Waterproofing and below-grade drainage systems were critical during the initial stages due to the high groundwater level, necessitating continuous dewatering during foundation installation. Once the foundation was secured, a robust concrete core system was erected using jump-form technology, ensuring the rapid and safe advancement of the central structural spine that houses elevator shafts and stairwells. Floor plates were constructed using post-tension concrete slabs to provide both structural efficiency and open interior layouts, with each floor carefully poured and cured in sequence, supported by a carefully orchestrated system of formwork and scaffolding. Given the height of the tower, wind loading and lateral forces presented significant design challenges. Structural engineers incorporated a combination of shear walls, outriggers, and a tuned mass damping system, if required, to manage building sway and ensure occupant comfort during high wind events. Cladding the exterior involved the use of high-performance glazing systems and curtain wall assemblies engineered to resist impact and water intrusion under extreme weather conditions. Mechanical, electrical, and plumbing systems were integrated vertically through centralized risers, while HVAC systems were selected to maximize energy efficiency and humidity control critical for the Florida climate. Interior fit-outs followed once the building was topped out, involving high-end finishes, smart home integration, and amenities such as fitness centers and rooftop lounges. Elevators, fire suppression systems, and life safety features were thoroughly tested and certified. Throughout the build, logistics were managed within a dense urban setting, requiring just-in-time delivery of materials and strict adherence to noise and traffic mitigation protocols. 400 Central stands as a prime example of modern high-rise construction adapted for the coastal southeastern United States, blending structural resilience with urban luxury living. The Howard Franklin Bridge expansion is a massive transportation infrastructure project aimed at increasing capacity and improving traffic flow across Tampa Bay, connecting Tampa and St. Petersburg via Interstate 275. Originally opened in the mid-20th century, the existing span has faced increasing congestion due to regional population growth, prompting the need for a new parallel structure. The expansion involves constructing a new bridge to the north of the existing southbound span, designed to carry 4 general-purpose lanes and 2 tolled express lanes in each direction, along with accommodations for bicycles and pedestrians. Site preparation began with detailed hydrographic surveys and subsurface geotechnical investigations to evaluate soil conditions and underwater topography. The bridge alignment crosses a broad expanse of open water, requiring hundreds of deep foundation elements such as large diameter-driven piles. These piles were installed using floating cranes and pile-driving barges, often operating in tandem to maintain schedule efficiency. Each pile was driven to a predetermined depth based on load testing and geotechnical analysis, ensuring adequate bearing capacity in the soft marine sediments characteristic of Tampa Bay. With foundations in place, construction moved to erecting the substructure, consisting of reinforced concrete piers supported by pile caps. These piers were cast using custom forms and high-performance concrete mixes designed for marine durability and resistance to chloride intrusion. Superstructure components included precast concrete beams and girders transported by barge from regional fabrication yards. These elements were lifted into place using heavy lift cranes and temporarily braced before the installation of cast-in-place deck slabs. The bridge deck was built in segments to allow for thermal movement, with expansion joints and post-tension tendons providing structural continuity and resistance to longitudinal forces. Given the environmental sensitivity of the bay, strict controls were enforced to prevent turbidity and protect marine habitats. Silt curtains, monitoring buoys, and coordination with environmental agencies ensured compliance throughout the construction process. Traffic staging and coordination with existing bridge operations were critical, as the adjacent spans remained in use during construction. Once the new span is completed, traffic will be rerouted, and the older southbound span is scheduled for demolition. The bridge is designed to current seismic and wind loading standards, with elevated profile grades and robust drainage systems to ensure resilience against storm surge and rising sea levels. Lighting, signage, intelligent transportation systems, and emergency pull-offs are also integrated into the final configuration. The Howard Franklin Bridge expansion exemplifies the challenges and precision required in modern bridge engineering over active waterways in densely populated regions. Riverfront Plaza in Jacksonville is a transformative redevelopment project situated along the St. Johns River in the heart of downtown. Formerly the site of the Jacksonville Landing, this new urban park and civic space is designed to integrate green infrastructure, community gathering areas, public art installations, and a landmark architectural feature into one continuous waterfront environment. The construction process for Riverfront Plaza is a blend of civil, landscape, structural, and utility engineering disciplines working together to reshape an iconic portion of the city's shoreline while addressing flood control, stormwater management, and long-term resilience. Demolition of the former structures marked the beginning of the project, involving selective deconstruction and recycling of building materials to minimize environmental impact. Once the site was cleared, geotechnical studies identified bearing capacity, soil composition, and potential contaminants from decades of prior development. Remediation work included soil stabilization, compaction, and in some areas, the replacement of substandard fill with engineered material to support hardscaping and load-bearing features. Perimeter erosion control and sediment fencing were installed to protect the adjacent river during earth-moving activities. One of the critical technical challenges was the elevation management of the plaza to accommodate both pedestrian use and flood mitigation. The design incorporates terraced levels and bioswales that direct stormwater away from heavily trafficked zones and toward vegetated catchment areas. Drainage infrastructure beneath the surface includes a network of perforated pipes, underdrains, and retention basins that allow water to percolate through soil media layers, reducing runoff and filtering pollutants before water reaches the river. Hardscape elements such as pathways, amphitheater seating, and event lawns are supported by concrete slabs and modular paver systems laid atop compacted sub-bases with integrated utility conduits for lighting, irrigation, and power supply. The installation of lighting poles, surveillance equipment, and public Wi-Fi access points was coordinated to minimize trenching and disturbance of landscaped zones. Foundation work for the signature art installation or vertical landmark structure included drilled concrete piers and anchorage systems capable of resisting wind and uplift forces, especially critical given the site's exposure to hurricanes and river breezes. The landscaping phase utilized native and adaptive plant species to create a biodiverse environment that requires minimal irrigation. Soil amendments, root barriers, and subsurface anchoring systems were used to ensure healthy tree growth while preventing root encroachment into hardscape zones. Installation of urban furniture, shade structures, and wayfinding signage followed, executed with precise alignment and coordination to maintain accessibility and sightlines throughout the plaza. Simultaneously, riverfront bulkhead repairs and reinforcements were conducted to address long-term shoreline erosion. These efforts included driving new sheet piles and installing riprap where necessary to stabilize the bank while integrating it visually with the park's design. All construction activities required ongoing coordination with municipal agencies, local businesses, and public stakeholders to manage access, maintain safety, and adhere to schedule constraints. Pendry Residences. Tampa is a luxury high-rise development currently under construction along Tampa's waterfront, representing a fusion of advanced residential tower engineering, mixed-use construction techniques, and coastal urban design. Rising prominently above the Riverwalk, this structure is planned as a combination of high-end condominiums and a luxury hotel, requiring a complex interplay between structural systems, vertical transportation logistics, and premium interior build-outs tailored to discerning occupants. The initial stages of construction began with detailed geotechnical studies to assess the subsurface conditions characteristic of Tampa's reclaimed and water-adjacent lands. Due to the potential for soft soils and high groundwater levels, the design necessitated deep foundations. Contractors deployed large rotary drilling rigs and pile-driving barges to install auger-cast piles or drilled shafts, ensuring that each foundation element penetrated down to load-bearing strata. Dewatering systems were concurrently operated to keep the excavation areas dry during the pile cap and mat foundation work. Sheet piling and temporary shoring systems enclosed the below-grade sections, allowing crews to safely form and pour the concrete base structures, including utility trenches and basement-level mechanical rooms. Once the substructure was complete, the superstructure advanced vertically using high-strength post-tension concrete slabs poured floor by floor in a sequential schedule coordinated with vertical formwork and scaffolding systems. The core of the building, housing elevators and stairwells, rose ahead of the floor plates using a jump-form system that provided both speed and rigidity. Because of the dual-use nature of the tower, serving both hotel guests and permanent residents, the mechanical and electrical design was bifurcated into separate but overlapping systems, each with isolated metering, HVAC zones, and fire suppression networks. Fireproofing, soundproofing, and vibration control systems were embedded throughout the vertical risers to isolate residential spaces from hotel operations. The building's facade was constructed using a curtain wall system comprised of high-performance, hurricane-rated glazing units and insulated aluminum frames. These were prefabricated off-site and installed via tower cranes and swing stages, allowing for a quick enclosure to facilitate interior trades. Inside, the fit-out involved bespoke finishes including imported stone, hardwood flooring, and integrated smart controls for lighting, climate, and security. High ceilings, expansive balconies, and floor-to-ceiling glass presented coordination challenges, especially regarding thermal insulation and waterproofing at slab edges and window junctions. Elevator cores were outfitted with high-speed lifts, some designated as private residential access with keycard control. Amenities such as rooftop pools, spas, lounges, and fitness centers required structural reinforcement in the upper levels to support the added loads from water tanks, equipment, and occupancy. These spaces were waterproofed with multi-layer membranes and tested for leakage prior to finish installation. Mechanical penthouses and rooftop equipment were enclosed in acoustically treated screen walls to reduce impact on nearby buildings. The logistical demands of building in downtown Tampa required precise coordination for crane positioning, material staging, and just-in-time delivery, with special consideration for pedestrian safety and traffic flow around the active Riverwalk. Permitting and inspections were rigorous due to the project's scale and waterfront proximity, involving compliance with city zoning, FEMA floodplain guidelines, and wind load requirements specific to Florida's Gulf Coast. Art House in St. Petersburg, Florida, is a contemporary high-rise residential tower designed to bring sophisticated urban living to the downtown waterfront. Rising prominently within the city's growing skyline, this tower combines modern architectural aesthetics with state-of-the-art structural systems and high-end residential amenities. From an engineering and construction standpoint, Art House presents a complex project involving deep foundation systems, vertical construction sequencing, and advanced building envelope technologies tailored to a subtropical coastal climate. The project began with comprehensive site preparation and geotechnical analysis to evaluate subsurface conditions typical of coastal Pinellas County. Due to the high water table and relatively soft soils in the area, a deep foundation system was required. Construction teams employed auger-cast piles or drilled shafts, installed using heavy drilling rigs equipped with continuous flight augers, which placed concrete and reinforcing steel deep into the ground to reach stable soil strata. Dewatering operations were necessary throughout foundation work, with well point systems operating continuously to maintain dry working conditions below grade. Once the pile caps and grade beams were completed, the project transitioned to vertical construction, starting with the building's reinforced concrete core. This central structural element was constructed using jump form systems, rising level by level ahead of the floor slabs. Each floor slab was built using post-tensioned concrete, providing long spans and open layouts ideal for luxury condominiums. Structural engineers designed the lateral load-resisting system with shear walls and moment frames to withstand wind pressures consistent with hurricane-prone areas. Mechanical, electrical, and plumbing systems were integrated through centralized vertical risers, with separate zones serving individual residential units. The HVAC system incorporated energy-efficient air handlers, dehumidification components, and smart thermostatic controls. Plumbing systems were pressure tested at each level, and sound insulation was installed around vertical ducts and pipe chases to maintain acoustic separation between units. The exterior cladding of Art House consisted of a high-performance curtain wall system and impact-rated glass, engineered to provide thermal insulation and wind resistance while maximizing panoramic views. Installation required the use of suspended platforms and tower cranes, with each unit sealed and waterproofed before interior work proceeded. Balcony structures were cantilevered and waterproofed using multi-layer membranes, with drainage integrated to manage Florida's heavy rainfall. Interior finishes followed a high standard, including European cabinetry, engineered hardwood flooring, quartz countertops, and custom lighting. Coordination of trades during the interior build-out phase was tightly scheduled, with finish carpenters, electricians, tile setters, and painters working in controlled sequences to meet aesthetic and performance standards. Fire protection systems, including sprinklers and emergency lighting, were installed and tested in compliance with local and national codes. The amenities level included a pool deck, fitness center, resident lounges, and workspaces, all requiring precise structural coordination to support loads from water, occupancy, and specialized equipment. Mechanical penthouses and service rooms were constructed on the uppermost levels, housing HVAC units, water heaters, and electrical switchgear, all enclosed within louvered screens for both visual appeal and sound attenuation. Logistics for the entire project were managed within the constraints of a dense urban environment. Construction staging, crane placement, material deliveries, and worker access were choreographed daily to minimize disruption to surrounding businesses and pedestrian pathways. Strict safety protocols and regular inspections ensured compliance throughout the build, with attention to stormwater runoff control and debris containment given the proximity to Tampa Bay. Horizon West Bay in Largo, Florida, is a mid-rise residential development constructed to deliver contemporary living accommodations within a growing suburban city center. Located near municipal and civic facilities, this project is emblematic of the new wave of urban-style residential buildings being introduced to smaller cities throughout the Sun Belt. The development integrates multiple levels of residential units with ground floor amenities and structured parking, requiring the coordinated use of mixed-use construction strategies, efficient structural systems, and infrastructure integration specific to the local climate and regulatory conditions. Construction began with extensive site clearing and grading, followed by geotechnical investigations to determine the bearing capacity of the underlying soils. Given the relatively flat terrain and shallow water table in the Largo area, slab-on-grade construction was ruled out for the upper levels, necessitating a more complex foundation solution. Engineers selected either shallow spread footings or a combination of grade beams and driven piles to support the superstructure, depending on the location within the site and the anticipated load distribution. Subsurface utility relocation was required early in the project, especially where stormwater drainage and sewer infrastructure intersected the future building footprint. Once the foundation was laid, construction transitioned to the vertical structural elements. Horizon West Bay employed concrete masonry unit, CMU walls, for structural partitions and exterior load-bearing components, combined with cast-in-place concrete slabs and precast concrete plank systems. This hybrid construction method balanced strength, cost efficiency, and fire resistance. Interior framing for unit walls and ceilings used metal studs and light-gauge steel tracks, allowing for faster mechanical and electrical installation across units. Mechanical systems were designed to accommodate Florida's humid climate, with each unit receiving a dedicated HVAC system featuring energy-efficient heat pumps, advanced filtration, and humidity control. Plumbing and electrical risers were centralized for ease of maintenance and constructed with noise-dampening measures to minimize acoustic transmission between floors and adjoining units. Fire safety systems included fire-rated walls, smoke alarms, sprinklers, and pressurized stairwells to meet all life safety codes for multifamily buildings. The building envelope was constructed with stucco-finished IFS cladding over a weather-resistive barrier, installed in layers to achieve both aesthetic appeal and energy performance. Window and door systems used insulated, low-emissivity, impact-rated glass to meet hurricane resistance codes while providing thermal efficiency. Roof systems incorporated rigid insulation and a reflective membrane to reduce heat gain and meet Florida's energy standards. Interior work proceeded as each floor was dried in, beginning with MEP rough-ins followed by drywall, flooring, cabinetry, and finish carpentry. Flooring materials included luxury vinyl plank and tile, selected for durability and ease of maintenance. Kitchens and bathrooms were fitted with solid surface countertops, undermount sinks, and energy-efficient fixtures. Common areas such as lounges, fitness rooms, and mail rooms were completed in tandem with residential units to ensure functional amenities at the time of occupancy. Structured parking was integrated into the building footprint, constructed using precast concrete panels and beams with a traffic-bearing waterproofing membrane. Lighting, security systems, and access control were embedded throughout the garage to ensure safety and usability. Site improvements included sidewalks, landscaping, stormwater detention ponds, and lighting fixtures designed for dark sky compliance. Civil engineering played a key role in integrating the development into Largo's municipal stormwater and transportation networks. The Sunrail Northern Extension to DeLand is a significant commuter rail infrastructure project expanding Central Florida's regional transportation network beyond its current northern terminus in DeBary. This extension involves upgrading an existing freight corridor owned by a Class 1 railroad to accommodate both passenger and freight operations. A complex endeavor requiring careful coordination, advanced civil engineering, and robust rail construction practices. Stretching approximately 12 miles, the extension is engineered to support high-frequency commuter trains while integrating with existing signaling, communications, and control systems already in operation along the rest of the Sunrail corridor. Construction began with comprehensive surveying and subsurface utility engineering to identify and avoid conflicts with buried infrastructure such as fiber optic lines, drainage culverts, and utilities paralleling the right-of-way. Track bed preparation commenced with clearing, grubbing, and regrading of the rail corridor to ensure proper drainage and subgrade stability. Where required, sub-ballast layers were improved or replaced using geotextiles and compacted granular material to ensure sufficient load-bearing capacity and long-term durability of the rail track structure. The single mainline track was upgraded using continuously welded rail, CWR, installed on concrete ties spaced and seated within a new bed of granite ballast. Rail sections were thermite welded in the field, followed by grinding and alignment to ensure smooth operation and minimize vibration. Ballast was placed in multiple lifts and tamped using automated machines that aligned and leveled the rail geometry to industry tolerances. Turnouts and crossovers were added strategically to allow passing operations and access to sidings, especially where freight and passenger train scheduling could potentially overlap. Bridge structures along the route, including culverts and overpasses, underwent inspection and, where necessary, rehabilitation to meet the higher loading standards required for passenger rail. Structural upgrades included concrete spall repair, bearing replacement, and in some cases, full superstructure reinforcement using steel plate bonding or carbon fiber wrap techniques. At-grade crossings were upgraded with new concrete panels, signal gates, and advanced train detection systems linked to positive train control (PTC) infrastructure to enhance safety and comply with federal mandates. The extension's new terminus at DeLand required the construction of a new passenger platform, parking area, and supporting infrastructure. The platform was built using precast concrete components, featuring tactile warning strips, lighting, canopies, and ADA-compliant ramps. Electrical and communications conduits were installed beneath the platform for future scalability. Adjacent facilities included a drop-off loop, pedestrian walkways, security systems, and stormwater management features designed to handle Florida's frequent rainfall. Signal system integration was a critical component of the project. Wayside signals, interlockings, and block detection systems were installed or modified along the route to provide seamless connectivity with the central dispatching system already managing Sunrail operations. Fiber optic cable was trenched along the corridor to provide real-time data transmission for PTC, train location monitoring, and emergency communication systems. Signal bungalows were prefabricated and installed on elevated concrete pads with backup power supplies to ensure system reliability during severe weather events. Construction operations were staged to minimize disruptions to existing freight traffic, requiring off-peak and nighttime work windows, flagging crews, and coordination with the freight operator to sequence activities without causing operational delays. Environmental protection measures were enforced throughout, including erosion control, wildlife protection plans, and careful management of work within wetlands and flood-prone areas. Permitting with state and federal transportation and environmental agencies was ongoing and comprehensive, reflecting the complexity of modifying an active rail corridor for dual-use functionality. Upon completion, the Sunrail Northern Extension to DeLand will provide vital transit connectivity to Volusia County, enhancing regional mobility while relieving highway congestion. American Dream Miami is an unprecedented megaproject designed to become the largest retail and entertainment complex in the United States. Located in northwest Miami-Dade County, the development spans hundreds of acres and merges commercial, recreational, and hospitality functions into a single, integrated site. The scale and ambition of the project require immense planning, phased construction sequencing, and coordination across multiple engineering disciplines including site civil works, structural engineering, vertical construction, and specialized systems for water management, traffic circulation, and energy efficiency. Site development began with mass grading and the relocation of existing utilities, involving the movement of millions of cubic yards of earth to create a stable foundation across what was once undeveloped wetlands and farmland. Environmental mitigation was a critical early-phase component. Stormwater management systems were engineered with massive retention ponds, underground vaults, and bioswales to comply with South Florida Water Management District regulations. Sheet piling, soil stabilization with lime or cement treatments, and perimeter berm construction were necessary to prepare the site for heavy vertical loads and to ensure long-term ground stability, especially for areas designated to house water parks, ski slopes, and multi-story structures. The project's structural layout includes a network of interconnected buildings varying in height and use. Foundations for these buildings were engineered with both shallow and deep systems, depending on geotechnical conditions. Large-span structures like indoor amusement parks, water parks, and retail atriums required specialized deep-pile foundations to resist settlement and lateral movement. Steel framing with long-span trusses was employed extensively to create the large open interiors essential for attractions like roller coasters and wave pools. These components were fabricated off-site and assembled using heavy-lift cranes with precise sequencing to minimize schedule conflicts and allow concurrent work across multiple zones. Mechanical, electrical, and plumbing systems were designed to support massive peak loads generated by climate-controlled recreational areas, retail tenants, and food service zones. Chilled water systems with rooftop cooling towers, variable air volume handlers, and extensive ducting networks were installed to maintain climate conditions in enclosed amusement environments. Plumbing systems had to accommodate both typical domestic demand and specialized functions like indoor snowmaking and large-scale aquatics, necessitating high-capacity pumps, filtration systems, and corrosion-resistant piping. Exterior cladding and roofing systems were selected for both performance and branding, with components such as tensioned fabric structures, glass curtain walls, and themed facades constructed using modular prefabrication techniques. Waterproofing and insulation were layered to account for Florida's heat, humidity, and storm events, with roof drains and overflow systems engineered to handle extreme rainfall. Vertical transportation systems including high-capacity elevators, escalators, and people movers were integrated throughout the development to ensure accessibility and circulation for tens of thousands of daily visitors. Parking infrastructure was another engineering feat. Multi-level garages and expansive surface lots were constructed using post-tensioned concrete decks and cast-in-place retaining walls. Traffic engineering played a central role in designing ingress and egress routes, integrating on-site roads with regional highways through new interchanges, signalized intersections, and bus terminals. Intelligent traffic systems, signage, and wayfinding elements were planned with simulation-based modeling to prevent congestion and facilitate smooth vehicular and pedestrian movement. Construction logistics for American Dream Miami required a scale of coordination typically reserved for industrial megaprojects. Material delivery schedules, workforce housing, staging zones, crane paths, and safety barriers were modeled in 4D simulations to ensure optimal site utilization and risk mitigation. Simultaneously, environmental monitoring was carried out to assess air quality, water runoff, and noise levels, with mitigation strategies applied continuously during active phases of work. Once operational, the facility is designed to handle millions of visitors annually, with systems in place for emergency response, life safety, and operational redundancy. The construction of American Dream Miami reflects the most complex integration of vertical and horizontal engineering in a commercial setting, representing a new generation of hybrid destination centers that merge entertainment, retail, hospitality, and infrastructure into a cohesive, engineered urban experience. The reconstruction of Tyndall Air Force Base in Panama City, Florida, is one of the largest and most advanced military installation rebuilds in modern U.S. history, driven by the extensive damage caused by Hurricane Michael in 2018. This reconstruction effort represents a long-term, multi-phase infrastructure and facilities redevelopment plan centered on resilience, mission readiness, and advanced technology integration. Designed to support next-generation fighter aircraft like the F-35, the effort required a complete reimagining of the base's built environment, including structural systems, utilities, flight line infrastructure, and storm-hardened facilities. Initial efforts began with damage assessment, site clearance, and debris removal, carried out by joint military and civilian engineering teams. Buildings deemed unsalvageable were demolished in a controlled sequence, with materials sorted for recycling or disposal. Simultaneously, civil engineers conducted a comprehensive geotechnical and hydrological survey across the installation to inform the design of new structures, utility corridors, and stormwater management systems. Much of the soil had to be reconditioned or replaced due to saturation and compaction caused by the storm, requiring stabilization techniques such as lime treatment, compaction grouting, and subgrade reinforcement using geosynthetics. The master plan for the rebuilt base incorporated distributed utilities, redundant systems, and hardened structures. Electrical infrastructure was placed underground where feasible to reduce vulnerability to wind and debris. Water, sanitary sewer, and communications networks were reconstructed using corrosion-resistant materials, with looped layouts allowing for continuous service during partial outages. Substations, lift stations, and control buildings were housed in wind and flood-resistant enclosures built to withstand Category 5 hurricane conditions. Vertical construction emphasized hardened concrete and steel structures with progressive collapse resistance, blast resistance, and full compliance with unified facilities criteria. Aircraft hangars were designed with clear spans exceeding 200 feet, supported by structural steel frames and braced bays. Roof assemblies used standing seam metal over insulated decking systems anchored with high-load mechanical fasteners and uplift rated to survive extreme wind events. Maintenance bays, munitions storage, and logistics centers were outfitted with reinforced concrete walls and storm-rated doors, ensuring continuity of operations during adverse conditions. Flight line reconstruction involved complete resurfacing of taxiways and aprons, the addition of new lighting systems, jet blast deflectors, and improved stormwater drainage. Concrete pavements were installed over stabilized subbases with expansion joints and reinforced panels capable of supporting repeated F-35 operations. Navigational aids and radar systems were relocated and shielded for increased survivability, while air traffic control towers were rebuilt with hardened glazing and backup power systems. Administrative and residential facilities were constructed with modular, energy-efficient designs, incorporating passive solar features, high-performance insulation, and low-impact development strategies. Barracks, dining facilities, and command buildings included progressive energy systems like solar photovoltaic arrays, advanced building management systems, and high-efficiency HVAC systems. Smart base technology was embedded throughout, including automated access control, video surveillance, and integrated cybersecurity protocols governing building automation and mission-critical systems. Logistics for the reconstruction were coordinated under a hub-and-spoke model, with central material laydown yards, controlled access zones, and precision delivery scheduling to manage the flow of construction equipment, materials, and personnel. Construction was executed in overlapping phases to allow ongoing base operations, requiring strict safety and coordination protocols. Federal, state, and local permitting was streamlined under mission priority guidelines, with environmental compliance maintained through on-site inspectors and adaptive sedimentation control measures. One Tampa is a high-rise residential tower under construction in downtown Tampa, Florida, set to become one of the tallest buildings on the city's skyline. This vertical development blends luxury condominium living with advanced structural engineering and urban construction logistics, standing as a significant example of high-density residential growth in a city undergoing rapid transformation. Its design calls for a slender tower profile supported by a heavily reinforced core and innovative construction methods to address both aesthetic goals and the complex engineering demands of building tall in a coastal, hurricane-prone environment. The project commenced with demolition and extensive site preparation in a tightly constrained urban setting. Excavation was limited due to surrounding structures and active utilities, requiring precision trenching and the use of engineered shoring systems to prevent soil collapse and protect adjacent property lines. Geotechnical analysis revealed a need for deep foundation systems, leading to the use of drilled shafts that extended well below the surface into competent limestone bedrock. Drilling rigs installed these caissons using slurry stabilization and steel reinforcing cages, followed by high-strength concrete pours to create vertical elements capable of supporting immense axial and lateral loads. With the foundation complete, the superstructure began with the central concrete core, which rises ahead of the surrounding floors. This jump-form core includes elevator shafts, stairwells, and service risers, and serves as the primary lateral load-resisting system. Around the core, post-tensioned concrete floor slabs are poured using flying formwork and edge protection systems, advancing at a pace of approximately one level every 5 to 7 days. Due to the tower's height and slender form, wind tunnel testing and computational fluid dynamics simulations were performed during design, resulting in the inclusion of outriggers and belt trusses at key levels to manage building sway and ensure occupant comfort under wind loading conditions. The building's facade consists of floor-to-ceiling glazing set within aluminum curtain wall panels engineered to resist hurricane-force wind and water intrusion. Each panel is installed from the outside using swing stages and sealed with silicone gaskets and pressure-equalized joints. Balconies are cantilevered from the slab edges and waterproofed using multi-layer membranes, with stainless steel railings and glass balustrades contributing to the tower's clean, modern appearance. Thermal performance and solar control are achieved through low emissivity coatings on all glazing. Mechanical, electrical, and plumbing systems are routed vertically through the core, with separate mechanical zones serving clusters of floors for optimal efficiency. High-efficiency HVAC units with variable refrigerant flow systems, energy recovery ventilators, and integrated building automation systems were installed to minimize energy use while maintaining indoor air quality. Electrical rooms and water risers are designed with redundancy, surge protection, and emergency power capabilities to maintain service continuity during outages. Interior construction is executed in phases as the structure rises. Once floors are enclosed, trades begin rough-in work for electrical, plumbing, and mechanical systems, followed by drywall, flooring, millwork, and finish carpentry. High-end finishes including stone countertops, engineered wood floors, designer lighting, and smart home integration systems are installed to meet luxury market expectations. Amenities such as a rooftop pool, fitness center, lounge areas, and business suites are distributed across podium and upper floors, each requiring specific structural and waterproofing provisions to support occupant loads, heavy equipment, and open water features. Construction logistics are tightly controlled due to the tower's location in a congested downtown area. A tower crane, material hoists, and just-in-time deliveries are coordinated to maintain workflow without obstructing public rights-of-way. A centralized construction management platform tracks progress, safety compliance, and material inventory in real time.
Construction of the Texas State Highway 365 tollway began with extensive site surveying and environmental assessments, given the area's sensitivity to both hydrological patterns and existing urban developments. Civil engineers first conducted geotechnical studies to determine the bearing capacity of the soil, as large portions of the alignment traversed alluvial plains with variable subsoil conditions. These studies inform the design of the subgrade and the depth of excavation required to create a stable foundation for the tollway structure. Once site clearing began, vegetation was removed, utilities were identified and either relocated or protected, and temporary erosion and sediment control measures were installed. Bulldozers, graders, and excavators were deployed in a phased manner to strip the topsoil, cut into embankments, and level the terrain. Given the proximity to flood-prone regions, extensive drainage infrastructure was integrated early in the grading process. This included the installation of reinforced concrete box culverts, precast stormwater inlets, and longitudinal storm sewer systems to manage runoff and prevent roadbed saturation. Next, the base layers were constructed. This began with the application of a geotextile fabric over weak subgrade areas to enhance load distribution. Crushed limestone was brought in and compacted in layers to create a high-density, non-expansive base that would support the weight of the pavement structure and vehicle loads. For quality assurance, nuclear density gauges and Proctor tests were used regularly to verify compaction levels. Concrete paving was selected for most of the tollway due to its longevity and load-bearing capacity. Slip-form pavers were employed to place continuously reinforced concrete pavement. This process involved laying down steel reinforcement, followed by the extrusion of concrete slabs, which were then textured and cured to ensure strength and skid resistance. Joints were carefully sawed at intervals to control cracking, and curing compounds were sprayed to prevent premature moisture loss. Parallel to the mainline construction, interchanges and ramps were built to facilitate connections with existing highways and local roads. These structures required drilled shaft foundations, formed and poured reinforced concrete columns, and precast concrete beams or steel girders, depending on the span and clearance requirements. Falsework and shoring systems were meticulously planned to support these structures during the erection phase, ensuring alignment and stability prior to concrete deck pours. Tolling infrastructure was integrated using overhead gantries equipped with electronic transponders and cameras. These systems were supported by underground conduits for power and fiber optic communication, which were installed prior to paving to avoid later disruption. Intelligent transportation systems, including variable message signs and traffic monitoring sensors, were installed along the corridor to support dynamic tolling and real-time traffic management. Safety features such as guardrails, crash attenuators, and high mast lighting were implemented throughout the corridor. Landscaping and revegetation of disturbed areas helped control erosion and restored the environmental buffer along the right-of-way. Once construction was substantially complete, final striping, signage, and pavement marking were applied, and punch list items were addressed before the tollway was open to the public.
The construction of One Manhattan Square, a luxury residential skyscraper located on the Lower East Side of Manhattan, required a carefully orchestrated approach to high-rise construction on a waterfront site with challenging geotechnical conditions and limited staging space. Rising over 800 feet in height, the tower features a slender profile and houses hundreds of residential units above a multi-level podium. The project involved extensive subsurface work, a reinforced concrete structural system, curtain wall facade installation, and the integration of extensive mechanical, electrical, and plumbing systems, all within the constraints of a dense urban environment. The first phase of construction focused on site excavation and foundation work. Given the site's proximity to the East River, groundwater management and soil stabilization were critical. Deep excavation was necessary to reach suitable load-bearing strata and accommodate below-grade parking and service levels. A perimeter slurry wall system was constructed to support the excavation and act as a long-term waterproofing barrier. This involved trenching around the site's perimeter, supporting the trench walls with bentonite slurry, and placing reinforcement cages followed by trammy concrete pours to form continuous wall panels. Within the slurry wall enclosure, mass excavation was conducted down to the foundation level. Dewatering systems using well points and sump pumps controlled groundwater intrusion, and real-time monitoring ensured excavation stability. The building's foundation consisted of a thick, reinforced concrete mat slab, designed to distribute vertical loads across the footprint while resisting hydrostatic uplift pressure. The mat was poured in large segments using high-strength concrete with admixtures to enhance durability and control curing. Vertical construction proceeded with the erection of a cast-in-place reinforced concrete superstructure. The building's structural system was composed of a central concrete core housing elevators, stairs, and mechanical risers, surrounded by perimeter columns and shear walls. The core was constructed using a jump form system, allowing continuous vertical progress while floor slabs were cast around it using flying formwork and table forms. Each floor cycle averaged several days with rebar post-tensioning cables and mechanical sleeve penetrations installed prior to concrete placement. High-strength concrete mixes were used to achieve the design compressive strength required for slender tower stability. Lateral loads from wind and seismic activity were resisted primarily by the stiffness of the core and the interaction of shear walls distributed along the tower's footprint. To reduce construction time, climbing formwork systems and tower cranes were deployed to support material delivery and personnel movement as the building rose. The tower's facade system featured a unitized curtain wall assembly composed of aluminum frames and insulated glass panels with low emissivity coatings. Each panel was fabricated off-site, pre-glazed, and tested for air and water infiltration before delivery to the site. Curtain wall installation occurred concurrently with structural work, with panels hoisted into position and anchored to embedded inserts at slab edges. The panels also included spandrel sections to conceal floor slabs and mechanical systems, providing a continuous visual envelope. Mechanical, electrical, and plumbing systems were routed vertically through dedicated shafts within the core and extended horizontally across each floor plate. The building's HVAC system relied on fan coil units and centralized chillers located in mechanical floors, supported by rooftop equipment and condenser water loops. Fresh air intake and exhaust systems were integrated into the facade using hidden louvers and custom architectural details. Plumbing systems were zoned by floor and included pressure-boosting pumps and backflow prevention devices to maintain consistent service across all levels. Electrical systems included dual utility feeds, on-site transformers, and emergency backup generators. Sub-metering was implemented to track usage by individual residential units, and distribution panels were installed in closets on each floor. Fire protection systems consisted of wet pipe sprinkler systems, standpipes, and fire alarm wiring, all coordinated using building information modeling to avoid conflicts with structure and finish systems. Interior fit-out began once the building envelope was enclosed and permanent power was established. Each residential unit featured gypsum board partitions, sound-rated floor assemblies, and high-end finishes including wood flooring, custom cabinetry, and stone countertops. Kitchens and bathrooms were prefabricated as modular assemblies where possible to accelerate installation and improve quality control. Energy-efficient appliances, LED lighting, and smart home technology were integrated into the units. Amenity spaces were constructed within the building's podium and included fitness areas, lounges, spa facilities, and entertainment rooms. These spaces required specialized mechanical zoning and sound isolation to provide acoustic comfort and performance. Finishes in these areas included acoustic ceilings, soft flooring, and decorative lighting systems. An exterior landscape terrace was built over the podium roof slab, incorporating lightweight fill, waterproofing membranes, and stormwater management features such as planters and drainage mats. Vertical transportation systems included high-speed elevators equipped with destination dispatch technology to reduce wait times and improve traffic flow. Elevator shafts were constructed using slip-form techniques within the core, and guide rails, cabs, and control systems were installed once the structure topped out. Life safety systems were interconnected through a central command center, with emergency lighting, public address systems, and integrated surveillance and access control equipment. Throughout construction, logistics were tightly controlled due to the site's urban setting. Deliveries were scheduled in narrow windows, materials were staged just in time, and vertical hoists and cranes were used to reduce on-site clutter. Coordination with city agencies ensured that street closures, utility connections, and construction access points were managed without disrupting surrounding traffic and pedestrian activity. The Bronx Point development is a transformative mixed-use project situated along the Harlem River waterfront in the South Bronx. Designed to anchor the revitalization of the Lower Concourse neighborhood, this project blends residential housing, public open space, cultural institutions, and retail infrastructure into a cohesive, community-oriented development.
Launching the Scottsdale Optima McDowell Mountain Village meant executing a large-scale, multi-building residential and mixed-use development in a sensitive desert environment, where sustainability, structural innovation, and logistical precision had to align from day one. Unlike conventional suburban construction, this project followed an integrated design-build model that required close coordination between architectural vision and structural implementation, from schematic design through vertical completion. Construction began with extensive site grading across the large footprint, but it also incorporated bioswale integration and retention basins to manage stormwater naturally. Earthwork included over-excavation beneath all building pads, followed by moisture conditioning and recompaction to meet strict geotechnical tolerances. Trenching for deep utilities came next, with parallel routing for chilled water, domestic water, fire protection, sewer, storm, and dry utilities such as power and communications. These were run in pre-planned corridors to serve each building efficiently without unnecessary excavation duplication. Optima's construction model leverages cast-in-place concrete systems extensively, and this village was no exception. Each residential tower utilized a podium-plus configuration, with subterranean parking garages acting as structural base levels. These below-grade levels were waterproofed with bentonite sheets and fluid-applied membranes before forming walls with high-density plywood systems. Vertical columns and shear walls extended through the podium to support the elevated post-tensioned slabs above. These slabs were poured in sequence using high-strength concrete, tensioned after curing to reduce cracking and allow thinner slab profiles, thereby reducing structural dead load and permitting taller floor-to-ceiling heights. Vertical cores for stairs, elevators, and utilities were slip-formed to accelerate progress, allowing parallel trades to begin rough-ins shortly after slab placement. Once the podium was completed, tower levels were constructed floor by floor in a tightly managed schedule. Mechanical, electrical, and plumbing trades were embedded early in the structure, using sleeve boxes, conduit blockouts, and prefabricated pipe racks lifted into place by tower crane. All ductwork was modeled using clash detection software, and fire-rated assemblies were coordinated with penetrations for seamless inspection approvals. Perhaps most distinctive was the incorporation of extensive rooftop gardens and planted balconies, all of which required complex structural planning to support soil loads, waterproofing protection, and integrated irrigation systems. A layered green roof assembly included root barriers, drainage mats, lightweight planting media, and capillary irrigation tubing tied to centralized water treatment systems that filtered grey water for non-potable reuse. Glazing systems were high-performance, thermally broken aluminum frames with low emissivity glass, designed to optimize daylighting while minimizing solar gain. Operable windows were integrated throughout, paired with sunshades, trellises, and balconies that added passive cooling elements. Exterior finishes blended textured concrete, steel mesh panels, and composite cladding materials, applied using suspended swing stages and mast climbers. Interior units followed a luxury specification with radiant floor heating systems embedded in gypcrete topping slabs, integrated lighting control systems, and floor-to-ceiling window walls. Amenities such as fitness centers, lap pools, spa zones, co-working lounges, and automated parking systems were incorporated directly into the podium and terrace levels, requiring close coordination between structural, architectural, and specialty contractors. All buildings were tied together with a shared energy and connectivity spine, linking data, security, fire alarm, and mechanical system controls through a centralized plant and digital management hub. The result was a self-contained, high-density residential complex that not only met structural and livability goals, but elevated the standard for sustainable urbanism in the Scottsdale region.
The expansion of the Tesla Gigafactory in Austin, Texas, officially known as Giga Texas, represents one of the largest and most advanced industrial construction efforts in the United States. Located along the Colorado River on the eastern edge of Austin, the site spans over 2,000 acres and serves as a central hub for Tesla's vehicle manufacturing, battery production, and future operations related to its energy and robotics divisions. The expansion of this facility has required large-scale site development, precision engineering, and massive logistical coordination to accommodate the simultaneous construction of multiple production lines and infrastructure systems. Site work began with extensive earth-moving operations to level the vast tract of land and prepare it for heavy industrial use. Bulldozers, scrapers, and excavators were used to move millions of cubic yards of soil, creating a flat and stable platform for foundations. Drainage swales, detention ponds, and underground stormwater systems were installed early in the process to manage runoff and prevent flooding, especially given the site's proximity to the river and its location within a region subject to periodic heavy rainfall. Foundation work for the expanded areas of the Gigafactory involved deep excavation and the construction of reinforced concrete footings, grade beams, and mats, due to the sheer size and weight of the industrial equipment housed within the plant, including stamping presses, casting machines, and robotic assembly lines. Foundations were engineered to extremely tight tolerances. Concrete was poured in large, continuous placements using high-performance mixes designed for strength and durability. Reinforcing steel cages were pre-tied on-site and lifted into place using tower cranes, ensuring consistency and efficiency in the foundation builds. The superstructure of the Gigafactory expansion primarily consists of a steel frame system with large-span girders and open-web joists designed to create wide, column-free interior spaces. This framing approach allows for maximum flexibility in arranging production lines and material handling systems. Structural steel components were fabricated off-site and delivered in sequenced loads for immediate erection. Multiple cranes operated in parallel to lift and set beams, columns, and roof trusses, with crews bolting and welding connections at a rapid pace to maintain schedule. Roof and wall systems are built with insulated metal panels and reinforced concrete tilt-up walls. The use of tilt-up construction provided a quick and durable solution for enclosing the facility. Panels were cast on site in horizontal beds, then lifted into place using specialized rigs and temporarily braced until tied into the structural steel frame. The exterior envelope includes large format glazing, roll-up industrial doors, louvers for mechanical ventilation, and embedded systems for future photovoltaic arrays. Internally, the facility is divided into multiple production zones, including body in white, paint, drive unit, battery cell, and final assembly areas. Each zone is outfitted with an integrated mechanical, electrical, and plumbing backbone tailored to the specific requirements of the manufacturing process. Electrical substations, bus ducts, and motor control centers distribute power to equipment, while compressed air, chilled water, and process piping systems run throughout the structure in overhead utility racks. HVAC systems consist of large rooftop air handling units with variable air volume controls and ductwork engineered for high-volume ventilation. Battery and paint shop areas are served by specialized air filtration systems and climate control to maintain environmental conditions necessary for quality control and safety. Fire protection includes wet pipe sprinkler systems, foam suppression in high-risk areas, and a network of fire alarm panels and detection devices distributed through ceiling and wall cavities. One of the most critical components of the expansion is the battery cell manufacturing area. This section requires ultra-clean environments, achieved through the use of clean room standards and enclosed spaces, positive pressurization, and air filtration. Mechanical isolation, anti-vibration pads, and precision leveling are incorporated into the floor systems to support sensitive equipment like electrode coating machines and cell assembly stations. Material movement throughout the Gigafactory is supported by automated guided vehicles, overhead cranes, and floor-mounted conveyors. These systems are designed to move components and finished products between zones without interfering with human workflow. Logistics tunnels, high bay racking systems, and buffer storage areas are constructed to support just-in-time delivery and reduce operational bottlenecks. The facility's expansion also includes workforce amenities such as office space, cafeterias, training rooms, locker facilities, and employee parking. These support structures are built using conventional steel framing and modular interior finishes. Elevated walkways and observation decks allow management and visitors to safely monitor operations while minimizing interference with production. On the exterior, the expansion incorporates new access roads, loading docks, and utility corridors. Heavy-duty concrete pavements are laid for truck traffic and equipment transport, while perimeter fencing, lighting, and security systems are installed to maintain site safety. Landscape buffers and erosion control measures are implemented to minimize environmental impact and comply with regulatory requirements. The Gigafactory expansion is managed using advanced construction technologies, including building information modeling, 4D scheduling, and real-time project tracking. Construction crews work in multiple shifts to maintain continuous progress, with prefabrication and modular construction methods employed to accelerate timelines.
Development of the Epic City project in Collin and Hunt counties began with an immense coordination effort across municipal boundaries, utility providers, and transportation agencies to ensure the foundational infrastructure could support the scale of this master-planned smart city. The first phase focused on land grading and hydrological management across several square miles of former farmland and low-density residential plots. Large-scale earth-moving operations utilize GPS-controlled bulldozers and motor graders to establish consistent elevation profiles for future roadways, drainage basins, and utility corridors. Extensive stormwater detention systems were constructed before any vertical development began. This included the excavation of retention ponds lined with clay and geotextile membranes, along with underground box culverts installed beneath arterial roadways to channel runoff to centralized treatment zones. Detention basins were designed with multi-stage outlet structures to regulate discharge rates during both minor and major storm events, protecting downstream ecosystems and adjacent urban infrastructure. The backbone of Epic City's build-out was its underground utility infrastructure, which included triple duct banks for electrical distribution, multi-conduit telecom pathways, and high-capacity water and sewer mains. Utility corridors were installed in coordinated trenches with separate elevation layers to avoid conflicts, and all infrastructure was mapped using RFID and GIS systems for ongoing asset management. Natural gas lines were routed with cathodic protection and above-ground isolation valves to enhance long-term safety and maintainability. The transportation grid was built from the ground up to support both traditional traffic and autonomous vehicle networks. Arterial roads featured full-depth concrete pavement with doweled contraction joints and integrated sensor arrays embedded at intersections to monitor vehicle flow and environmental conditions. Roundabouts, smart traffic signals, and vehicle-to-infrastructure communication beacons were included as part of the Intelligent Transportation System deployment. Dedicated lanes for high-occupancy vehicles, electric buses, and autonomous delivery pods were constructed alongside main boulevards using contrasting pavement materials for clear lane identification. Vertical construction followed a hybrid model of traditional steel and concrete buildings and modular prefabrication. Commercial and civic buildings were erected using steel frames and precast concrete panels, while some residential structures utilized factory-assembled wall panels and floor cassettes to speed construction cycles. Building foundations incorporated post-tension slabs in high-traffic zones and pier-supported grade beams in areas with variable soil profiles. Each district of Epic City was designed with integrated energy systems. Distributed energy resources such as rooftop solar, battery storage, and thermal energy networks were connected to a centralized microgrid, allowing for localized energy balancing and off-grid operation during outages. Substations were constructed with switchgear housed in blast-rated enclosures, and each neighborhood included EV charging stations integrated into the sidewalk infrastructure. Water reuse systems were embedded into the municipal plumbing network, with dual pipe systems carrying reclaimed water for irrigation and cooling uses. Smart metering, automated leak detection, and flow regulation valves enabled real-time water management across residential and commercial zones. Public realm enhancements included bioswale-lined streets, shaded pedestrian corridors, and precast concrete pavers with embedded LED lighting for wayfinding and safety. All components were coordinated through a centralized digital twin of the city, allowing planners, engineers, and operators to visualize, monitor, and manage the complex infrastructure in real time as Epic City rose from concept to livable urban reality.
The Hudson Tunnel Project, part of the broader Gateway program, represents one of the most critical infrastructure efforts in the northeastern United States, designed to create a new two-track rail tunnel beneath the Hudson River connecting New Jersey to Manhattan. This massive undertaking involves constructing an entirely new tunnel system, rehabilitating the existing North River tunnels, and upgrading related infrastructure to enhance capacity, reliability, and resiliency for Amtrak and New Jersey transit operations. Given the complexity of tunneling beneath a river in a densely urbanized corridor, the project requires advanced geotechnical planning, innovative construction methodologies, and rigorous logistical coordination. The construction of the new Hudson Tunnel begins with the establishment of tunnel portals on both the New Jersey and Manhattan sides. On the west side, in North Bergen, site preparation includes clearing a large staging area, relocating utilities, and driving deep foundations for the tunnel entrance structure. This involves the use of soldier piles and lagging systems to create excavation support for the open-cut sections of the tunnel approach. The excavation is conducted in phases, with groundwater control measures such as weld points and deep wells installed to stabilize the soil and lower the water table. On the Manhattan side, the tunnel emerges beneath Hudson Yards, requiring intricate coordination with existing foundations, utilities, and operational rail infrastructure. Access shafts and launch boxes are constructed using slurry wall and secant pile techniques to create watertight enclosures. These structures serve as both tunnel access points and critical infrastructure for ventilation and emergency egress. Dewatering systems and continuous monitoring are essential throughout the excavation process to prevent settlement or structural damage to nearby buildings. The main tunnel drive is carried out using pressurized face tunnel boring machines, or TBMs, specially designed to operate in mixed face conditions comprising soft soils, silts, and bedrock. Each TBM is equipped with a rotating cutter head, shield, and trailing support systems that handle spoil removal, segment installation, and auxiliary systems. The TBMs are launched from the New Jersey side, advancing eastward beneath the Palisades, the Hudson River, and into Manhattan. As the machines progress, they install precast concrete segments to form the tunnel lining. Each ring comprises several curved segments with waterproof gaskets bolted and grouted in place to create a continuous sealed tunnel shell. Spoil material generated by the TBMs is transported via conveyor belts or muck trains to the portal areas for removal and disposal. The tunnel boring process is carefully monitored using automated systems that track TBM position, face pressure, cutter wear, and ground movement. Data is relayed to control rooms where engineers can adjust parameters in real time to optimize performance and mitigate risks. Once the twin bores are completed, a range of secondary construction activities takes place inside the tunnels. This includes the installation of track bed systems, drainage lines, utility conduits, and concrete walkways. A concrete invert is poured to create a flat surface for ballastless track systems, typically slab track, which ensures high-speed stability and reduced maintenance. Third rail or overhead catenary supports are anchored to the tunnel lining, depending on the electrification method used. Signal cable trays, fiber optic communication lines, and fire detection systems are integrated along the tunnel interior. Mechanical and electrical systems include powerful ventilation fans housed in dedicated shafts, designed to maintain air quality during regular operations and to evacuate smoke in the event of fire. Emergency lighting, evacuation signage, and public address systems are installed throughout the tunnels, with cross passages between bores spaced at regular intervals to facilitate emergency egress and firefighting access. At each tunnel portal, substations and switchgear are constructed to supply power to trains and tunnel systems. These facilities include redundant transformers, switchboards, and backup power sources such as diesel generators and uninterruptible power supplies. The entire tunnel is connected to a centralized control system that monitors train movement, environmental conditions, and system performance in real time. Simultaneously with the construction of the new tunnel, the project involves the future rehabilitation of the existing North River tunnels, which suffered saltwater damage during Hurricane Sandy and continue to degrade. Once the new tunnel is operational, rail traffic will be rerouted through the new bores, allowing the old tunnels to be taken offline sequentially for full restoration. This process includes the removal of deteriorated track systems, replacement of corroded bench walls, structural repairs to the concrete liner, installation of modern waterproofing membranes, and upgrades to all mechanical and electrical systems. The Hudson Tunnel project also incorporates track realignments and yard reconfigurations on both sides of the river. In New Jersey, additional work includes the construction of approach structures and flyovers to integrate the new tunnel into existing Amtrak and NJ transit lines. In Manhattan, the connection involves carefully threading the new tracks into Penn Station's complex and congested rail throat. This necessitates new signal interlockings, turnout installations, and extensive coordination with other rail improvement projects in the area. Environmental mitigation measures are implemented throughout construction to protect water quality, air quality, and adjacent ecosystems. These include sediment control barriers, air filtration for construction sites, and noise suppression systems. Special consideration is given to minimizing disruption to local communities and existing transportation networks.
Bringing TSMC Fab 21 to life in North Phoenix demanded one of the most technically advanced semiconductor facility builds in the United States. This megaproject required a fusion of high-precision cleanroom construction, utility-heavy support infrastructure, and robust seismic and environmental engineering solutions, all executed on a tight timeline within a desert environment. The development began with mass grading across hundreds of acres to establish a stable platform for both the fab itself and the sprawling central utility building, administration spaces, and logistics hubs. Earth-moving operations required both over-excavation and recompaction to meet rigorous load-bearing criteria, particularly for the cleanroom slab, which must maintain a virtually zero tolerance for differential settlement. Vibration mitigation began at the soil level, where layered sub-base configurations and damping materials were installed to reduce micro-vibrations that could interfere with nanometer-scale lithography. Foundation work incorporated a network of heavily reinforced mat slabs and pile caps. In certain zones, deep foundations were installed using auger cast piles to transfer loads well below any compressible strata. The main fab structure was built using steel moment frames and composite metal deck slabs, designed to support not only the cleanroom above, but also extensive overhead mechanical and process utilities routed through a heavily loaded interstitial floor. Cleanroom construction demanded extreme precision. Raised access flooring allowed for laminar airflow, while walls and ceilings were clad in non-shedding, chemically resistant materials. Every seam, panel joint, and utility penetration was sealed to ISO standards, with HEPA filter housings integrated into a grid of fan filter units in the ceiling plenum. Environmental conditions, temperature, humidity, and airborne particle count had to remain within ultra-narrow tolerances, requiring redundant HVAC systems, deionized water production units, and high-efficiency gas scrubbers. The scale of process utility integration was immense. An underground pipe rack corridor was constructed to distribute ultra-pure water, specialty process gases, slurry lines, vacuum systems, and chemical waste returns. All pipe systems were color-coded and installed with leak detection, double containment, and purge capability. Above-ground utility bridges spanned between the central utility plant and the fab, carrying high-volume, chilled water, nitrogen, and clean dry air lines across multiple levels. The central utility building itself was a complex of power transformers, chillers, boilers, air compressors, and chemical delivery systems. Redundant backup generators and uninterruptible power supplies were installed to ensure zero downtime in critical process areas. High-voltage electrical rooms were isolated with arc flash rated enclosures, while transformers and switchgear were mounted on isolated slabs to prevent mechanical vibration transmission. Environmental compliance drove the inclusion of advanced waste treatment facilities and air emissions controls. Scrubber stacks, flare systems, and liquid neutralization tanks operated around the clock to process both hazardous and non-hazardous waste streams. Permitting required continuous environmental monitoring and real-time reporting capabilities. Security and access control were embedded into the site design. Guardhouses, secure perimeters, and biometric access zones were installed to protect intellectual property and personnel. The internal circulation of materials followed a just-in-time logistics model, supported by automated guided vehicles and robotic systems operating in designated corridors beneath the cleanroom floor.
The O'Hare 21 terminal expansion is a transformative aviation infrastructure program designed to reimagine Chicago O'Hare International Airport for the demands of 21st century air travel. At the heart of the program is the replacement and expansion of Terminal 2 with a new global terminal, along with the construction of 2 new satellite concourses and extensive modernization of existing terminal facilities. This multi-billion-dollar initiative involves complex phasing, advanced construction techniques, and tight coordination with airport operations to ensure uninterrupted service throughout the project's delivery. Site preparation began with the demolition of ancillary buildings, relocation of utilities, and reconfiguration of aircraft taxiways and service roads surrounding Terminal 2. Given the proximity to active runways and operational terminals, safety and logistics planning were paramount. Construction staging areas were established on airside and landside zones, complete with dust control systems, lighting, fencing, and noise monitoring. Crews implemented an array of protective measures to shield live taxiways, including jet blast deflectors, reinforced barriers, and safety exclusion zones. The replacement of Terminal 2 with the new O'Hare Global Terminals required complex foundational engineering to support a significantly larger and more structurally ambitious building. The substructure design utilized a grid of deep foundations composed of drilled shafts extending into glacial till and bedrock, with pile caps and grade beams forming the structural base. The mat foundation was poured in large segments with high-strength concrete using thermal control techniques to manage the heat of hydration and ensure structural integrity. The global terminal's superstructure consists of long-span steel framing, using massive plate girders and trusses to create column-free interior spaces for check-in, security, and baggage handling areas. The design required the prefabrication of structural steel assemblies off-site and timed delivery for erection using tower cranes and mobile lifting equipment. Steel members were connected using high-strength bolts and full penetration welds, with temporary bracing to stabilize the frame until the diaphragm action of the floor slabs was established. Curved roof geometry and soaring ceiling heights define the architectural vision for the terminal. The roof system uses a series of structural arches and purlins supporting metal decking and multiple layers of insulation, waterproofing, and reflective membrane roofing. Skylight assemblies, suspended from trusses, bring daylight into the terminal's core, and were installed using swing stages and engineered rigging plans. The two satellite concourses are connected to the global terminal via underground pedestrian tunnels, constructed using cut-and-cover techniques and temporary earth retention systems. These tunnels house moving walkways, mechanical and electrical systems, and emergency egress paths. Utility corridors beneath the tunnels carry chilled water, fire suppression, data cables, and potable water piping from the central utility plant to each concourse. Terminal interiors are being built with modular construction techniques to allow rapid deployment and future flexibility. Raised access flooring systems provide underfloor distribution for power, data, and HVAC, supporting quick tenant turnover and reconfiguration. High-performance glazing systems are installed on the terminal facades to improve thermal comfort and reduce energy loads. These systems feature low emissivity coatings, thermally broken aluminum frames, and automated sunshades responsive to solar orientation. Mechanical, electrical, and plumbing systems are integrated into the terminal's core and distributed across vertical and horizontal chases. The HVAC design includes dedicated outside air systems with energy recovery ventilators, variable air volume units, and high-efficiency chillers linked to a central plant. The electrical backbone includes redundant switchgear, generator backup, and uninterruptible power supply units for critical systems such as flight information displays, security, and baggage handling. The baggage handling system spans the new global terminal and the satellite concourses, incorporating inline explosive detection screening, high-speed conveyors, and smart routing software. The system is built within a multi-level service zone and coordinated in detail using building information modeling to avoid clashes with structural and mechanical elements. Tilt tray sorters and destination-coded vehicle systems ensure rapid and accurate baggage movement across large distances. Airside infrastructure includes new aircraft gates with dual jet bridges, apron repaving, and reconfigured taxi lanes. Jet fuel hydrant lines are installed below the apron, connected to the airport's fuel farm via loop distribution mains. Each gate is equipped with ground power units, preconditioned air, and visual docking guidance systems, integrated into a digital apron management system that coordinates aircraft movements and turnaround operations. Passenger experience enhancements include expanded security screening zones with automated screening lanes, centralized customs and immigration processing, and intuitive wayfinding systems. Vertical circulation is handled through panoramic elevators, escalators, and stairs connecting multiple terminal levels. Concession and retail zones are constructed with pre-engineered kiosk platforms and coordinated MEP stubs, allowing rapid fit-out and tenant flexibility. Throughout construction, phasing and operational continuity are managed using detailed sequencing plans, temporary passenger corridors, and modular temporary facilities. Security zones are maintained with physical barriers, credentialed access, and 24/7 surveillance. All work must comply with Federal Aviation Administration regulations and be coordinated with the Transportation Security Administration and Air Traffic Control.
Launching the Austin-Bergstrom International Airport expansion required a meticulously phased approach to integrate new facilities without disrupting ongoing operations. The initial stages focused on enabling works, including rerouting of utilities, relocation of existing service roads, and reinforcement of airside security perimeters. Survey crews used LiDAR and ground-penetrating radar to map existing underground infrastructure and coordinate precise tie-ins with the new systems. Temporary construction access points were established, and logistic staging areas were demarcated to accommodate a steady flow of materials, heavy equipment, and prefabricated assemblies. Foundation work for the new terminal sections, concourses, and utility buildings involved deep excavation and concrete piling. Soil conditions near the former military airbase zones necessitated dynamic compaction in some sectors to stabilize the subgrade. Once load-bearing conditions were confirmed, pile caps and grade beams were poured using high-performance concrete. Reinforcement detailing was designed to account for seismic, wind, and thermal stresses typical of large-span airport structures. The superstructure utilized a combination of structural steel framing and long-span trusses to create open interior volumes for the new concourses. Prefabricated steel components were erected using crawler cranes with sequential bolting patterns and diagonal bracing to maintain geometric alignment. Above the passenger areas, a lightweight roof system integrated insulated metal panels and skylights to introduce natural light while meeting thermal and acoustic insulation standards set by FAA and LEED requirements. Interior slab-on-deck pours were coordinated with embedded conduit runs for electrical and data distribution. Elevated mechanical mezzanines were constructed to house air handling units, VAV boxes, and ductwork runs that supplied the expanded terminal zones. HVAC systems were zoned for redundancy and integrated into the airport's existing energy management system. The use of underfloor air distribution in certain gates improved thermal efficiency and passenger comfort. New baggage handling systems were implemented beneath the terminal deck, including high-speed conveyor belts, RFID tagging stations, and inline explosives detection machines. These systems were supported by structural trenches and service catwalks, allowing maintenance crews full access during operations. The installation followed a phased commissioning schedule to maintain the functionality of existing carousels while integrating the new loops. Airside expansion included the extension of taxiways and aircraft apron areas, using Portland cement concrete pavement with deep dowel baskets and expansion joints designed for wide-body aircraft loads. Precision laser grading ensured consistent pavement elevation, and pavement marking was performed with high reflectivity thermoplastics for visibility in adverse weather. Jet bridges and ground support infrastructure were pre-installed on apron pads before gate commissioning. The new concourses were fitted with advanced security screening areas, including automated tray return systems and computed tomography scanners for carry-on luggage. Passenger amenities such as lounges, concessions, and smart wayfinding kiosks were installed with integrated digital infrastructure. This required robust Wi-Fi, Bluetooth beacon arrays, and digital signage mounted throughout the terminal core and satellite areas. To close out the expansion, life safety systems, including fire alarms, emergency lighting, and evacuation audio, were tested under full operational loads. Airport staff underwent simulation-based training in the new spaces, while system-wide performance tests validated HVAC loads, electrical grid balancing, and communications interoperability. With the completion of the expansion, Austin Bergstrom was equipped to handle future demand increases with improved passenger flow, aircraft accommodation, and operational resilience.
The construction of the new Highmark Stadium in Orchard Park, New York, the future home of the Buffalo Bills, involves the development of a modern open-air sports facility designed to enhance fan experience, operational efficiency, and long-term durability in a region known for its severe winter conditions. This multi-year, multi-billion-dollar project is being built adjacent to the existing stadium, allowing uninterrupted use of the current facility during construction. The project requires extensive coordination of site development, structural engineering, vertical construction, mechanical systems, and logistics in order to deliver a stadium suited for National Football League operations and year-round community use. The site work began with extensive geotechnical surveys and soil borings to determine subsurface conditions. Given the clayey soils and shallow groundwater common in the region, the stadium's foundation system was designed to include deep foundations consisting primarily of driven steel piles and reinforced concrete drilled piers. These foundation elements extend to layers of dense till or weathered bedrock to ensure settlement control and resistance to frost heave, a key concern in the region's freeze-thaw cycles. Foundation work also included pile caps and grade beams, which tied together vertical loads from superstructure columns and distributed them into the subgrade. Following earthwork and foundation construction, the stadium's structural system began rising from the ground. The primary vertical and lateral force-resisting systems are composed of structural steel frames using wide flange beams, box columns, and truss members to accommodate large spans over seating bowls and concourse levels. Erection of steel components was carried out using crawler cranes, mobile tower cranes, and temporary bracing towers to stabilize elements until permanent connections were completed. Bolted connections predominated for speed and ease of assembly, with some welded joints required for moment-resisting frames in the main concourse and canopy structures. The stadium features a continuous seating bowl with multiple tiers, supported by cast-in-place concrete raker beams and precast concrete treads and risers. These structural components were manufactured off-site and trucked in for installation, using heavy-duty lifting equipment. Precast elements were aligned and shimmed into place, then grouted and anchored to ensure a rigid connection to the supporting steel or concrete framework. Vomitories, stairs, and circulation corridors were integrated into the bowl structure, incorporating slip-resistant coatings and embedded tactile strips for accessibility compliance. A prominent feature of the stadium is its canopy structure, which is designed to cover a significant portion of the spectator seating while remaining open at the field level. The canopy is supported by long-span cantilevered trusses projecting from the outer edge of the upper seating bowl. These trusses were fabricated in segments and lifted into position, then post-tensioned to reduce deflection and improve load transfer. The canopy cladding includes metal panel systems and translucent roofing materials to allow natural light penetration while providing shelter from rain and snow. Snow load considerations were a primary design constraint, requiring robust framing and drainage systems to prevent ice accumulation and structural overstress. Mechanical systems within the stadium include air handling units, hydronic heating systems, and ventilation equipment tailored to the open-air nature of the venue. Large mechanical rooms were installed beneath the seating bowl and in service cores, housing boilers, pumps, and fan systems. Given the region's cold climate, radiant heating systems were embedded into portions of the concourses and key field-level areas to prevent freezing and ensure operational continuity. The field itself incorporates a subgrade heating system to prevent turf freezing and ensure safe playing conditions during late season and playoff games. Electrical systems included high-capacity feeders, switchgear, and lighting panels distributed through electrical closets and conduits hidden within wall cavities and floor trenches. LED lighting systems were installed throughout the stadium, including field lighting, which was mounted on the canopy structure to provide even illumination with minimal glare. Emergency power systems, including diesel generators and battery-backed UPS systems, ensure continuity of life safety and broadcast operations during outages. The stadium's vertical circulation is supported by escalators, elevators, and wide staircases, designed to handle rapid ingress and egress of over 60,000 spectators. Vertical cores were constructed using reinforced concrete shear walls with embedded elevator guide rails and MEP chaseways. All passenger elevators were installed with regenerative drives and machine roomless technology to reduce energy use and maintenance demands. Within the stadium envelope, premium seating areas, suites, clubs, and press facilities were constructed using structural framing and high-end interior finishes. These spaces included raised access floors, custom millwork, acoustic ceiling systems, and advanced audiovisual integration for real-time data display and broadcast capabilities. Extensive mechanical zoning and separate air handling units were used to isolate VIP areas from general circulation zones. On the exterior, the stadium design incorporates architectural metal panels, stone veneer, and curtain wall glazing in key entry points. Exterior plazas and arrival zones were constructed with reinforced concrete pavement, pavers, and landscape features, including stormwater planters and snow melt systems embedded in walkways. Security measures such as bollards, surveillance systems, and controlled entry points were coordinated with structural and civil design. Logistics played a central role throughout the construction process. Given the tight construction schedule, materials were procured using just-in-time delivery methods with on-site laydown areas minimized through advanced planning. Winter construction required temporary enclosures, heated work areas, and cold weather concrete practices, including admixtures and thermal blankets.
Construction of the VI Resort in Glendale unfolded as a complex hospitality and entertainment project requiring meticulous sequencing across multiple concurrent workstreams. Rather than a single structure development, this resort was conceived as a multi-building campus featuring a luxury hotel tower, indoor and outdoor concert venues, water attractions, retail and dining spaces, and a central lagoon, each element demanding its own set of structural and systems engineering approaches. The site preparation phase began with mass excavation to create space for underground parking and mechanical service corridors. Soil stabilization involved lime treatment in select areas to improve load-bearing characteristics, followed by the placement of geotextile fabric and compacted fill. The lagoon basin required a deeper excavation profile, finished with a reinforced concrete liner and waterproofing membrane to contain the water feature without seepage. Adjacent utility trenches were routed to accommodate filtration lines, electrical conduits, and pump intakes, all laid in accordance with hydrodynamic modeling for optimal water circulation. The resort's signature hotel tower rose from a spread footing foundation system tied together with continuous grade beams. Above that, the structural system transitioned to a cast-in-place concrete core with post-tensioned concrete slabs, allowing for long-span floor plates and column-free views for premium guest rooms. Creep and shrinkage of the slabs were modeled early to account for deflection and ensure precise placement of embedded sleeves and anchor points for curtain wall systems. The exterior facade used a combination of unitized aluminum glazing systems and rain screen metal panels installed via swing stage access from the tower's perimeter scaffolding. Simultaneously, the concert amphitheater was constructed with a structural steel skeleton, integrating trusses that spanned the entire stage and canopy area. Acoustic isolation pads and vibration damping systems were embedded into the structure to reduce transfer to the surrounding resort zones. Back-of-house areas included electrical rooms with stage lighting control panels, audiovisual distribution rooms, and dock access for touring vehicles. Amphitheater seating was cast in place in a raked configuration with egress paths designed to flow directly into landscaped promenades. Special attention was paid to the lagoon-side entertainment areas, where boardwalks, cabanas, and overwater structures required deep-driven steel piles and precast concrete caps. These were connected by engineered wood decking that resisted UV exposure and thermal expansion. Integrated lighting and sound systems were embedded into the hardscape with low-voltage conduits routed through waterproof junction boxes mounted beneath structural supports. Mechanical and electrical systems across the site were integrated through a central utility core, with chilled water and emergency power distributed through a looped system. Energy efficiency was prioritized with variable speed drives, economizer cycles, and advanced building automation controls. Each building was modeled thermally to optimize glazing ratios, shading structures, and HVAC zoning. Kitchen exhaust systems, grease interceptors, and commercial water heaters were installed in the back-of-house areas for food and beverage operations.
The GreenLink West transmission line is a major electrical infrastructure project in the state of Nevada, designed to enhance grid reliability, support renewable energy integration, and increase transmission capacity across the western region of the state. Developed by NV Energy, this transmission corridor spans approximately 300 miles, connecting the Las Vegas area in the south to the Fort Churchill substation near Yerington in the north. The project represents a foundational component of Nevada's broader GreenLink Nevada initiative, intended to transform the state's electrical grid and facilitate access to clean energy resources while improving resiliency and operational flexibility. Construction of the GreenLink West project begins with detailed route planning and environmental assessment as the alignment traverses vast expanses of public and private land, including Bureau of Land Management territory, tribal lands, and rural communities. Environmental permitting requires in-depth analysis of habitats, cultural resources, hydrology, and visual impacts. Once regulatory approvals are secured, fieldwork starts with land surveying, geotechnical borings, and the establishment of construction access routes. The transmission line itself is a high-voltage 525 kilovolt alternating current system using steel lattice towers and monopole structures, depending on the terrain and land use considerations. The design of the transmission line takes into account topography, wind loading, seismic considerations, and conductor sag. In mountainous areas, lattice towers are selected for their ability to span long distances and provide greater stability. While in open desert or agricultural zones, tubular steel monopoles are often preferred for their smaller footprint and faster installation. Foundation construction for each transmission structure is highly site-specific. In rocky or uneven terrain, drilled pier foundations are used, where holes are bored into the ground and filled with reinforced concrete. In softer soils, direct embed foundations or grouted steel shafts may be employed. Reinforcing steel cages are fabricated and placed on-site with concrete delivered by ready-mix trucks or mobile batch plants established along the corridor. Anchor bolts are set with tight tolerances to ensure the precise alignment of tower base plates. Tower erection involves lifting pre-assembled sections using crawler cranes, hydraulic booms, or helicopter lifts in remote or inaccessible areas. Each tower section is bolted together in sequence and alignment is checked at each stage. Conductor stringing follows tower installation and is conducted using tensioning and pulling equipment to carefully manage the weight and sag of the heavy aluminum conductor steel reinforced cables. Multiple phases of conductors are strung along with shield wires for lightning protection, and optical ground wires are installed to enable real-time monitoring and communications. Substations at each end of the Greenlink West Line are upgraded or newly constructed to accommodate the increased voltage and new circuit paths. At these substations, high-voltage breakers, transformers, reactors, and switchgear are installed on reinforced concrete pads, protected by gravel surfacing and perimeter fencing. Buswork, insulators, and control cabling are arranged to allow for flexible operation and maintenance. And relay protection systems are programmed to detect faults and isolate them within milliseconds. To support future energy development, tap points and interconnection bays are integrated into the transmission design, allowing new solar, wind, and geothermal projects in central and western Nevada to tie directly into the grid. The transmission line is also engineered with N1 reliability criteria, meaning the system can continue operating even in the event of a single component failure, an essential feature for ensuring consistent power delivery in extreme weather or emergency conditions. Throughout construction, environmental mitigation measures are implemented to protect wildlife, water quality, and cultural resources. This includes installing erosion control barriers, wildlife exclusion fencing, and temporary bridging at stream crossings. Dust suppression is carried out with water trucks, and sensitive areas are avoided or monitored with environmental inspectors present during construction. When work is completed, disturbed areas are regraded and revegetated with native plant species to restore habitat and minimize erosion. Workforce logistics are a significant consideration given the remote nature of much of the route. Mobile staging yards, equipment laydown areas, and temporary access roads are established at intervals to support material delivery and worker access. Helicopter operations are scheduled to transport components and personnel to difficult-to-reach locations, especially in rugged mountainous zones where road access is limited or environmentally restricted. Digital construction management tools, including GIS-based routing systems, remote sensing data, and real-time construction monitoring platforms, are employed to coordinate crews, document progress, and track compliance with safety and environmental requirements. A central command center oversees construction phasing and coordinates with utility operations to avoid service disruptions and ensure synchronization with other grid infrastructure projects.
When construction commenced on the X-Energy and Dow Small Modular Reactor Nuclear Plant in Seadrift, Texas, it marked the integration of advanced nuclear technology within a chemical manufacturing complex. The site selection process prioritized co-location with industrial thermal demand, as the SMR units were designed not only to generate electricity, but also to provide high-temperature steam for Dow's process operations. The initial site preparation involved clearing and grading a large area adjacent to existing infrastructure, with heavy emphasis on creating a stable platform free of differential settlement risks. Soil stabilization was performed using lime treatment, and deep foundation work began with auger cast piles to support critical structures, including reactor containment buildings and turbine halls. The nuclear island construction required a precision-driven sequence of activities. Reinforced concrete foundations were laid for each reactor module, incorporating dense rebar mats and embed plates to support seismic resistance and load transfer. The containment vessel for each SMR unit was fabricated off-site and delivered in modular sections. These modules were lifted into place using heavy lift cranes and positioned within a below-grade reactor cavity formed by cast-in-place concrete with multi-layer waterproofing and radiation shielding components. Each containment structure included integrated penetrations for coolant loop connections, sensor conduits, and control rod drives. Structural liners were welded internally to provide a leak-tight barrier, while the reactor core itself, pre-assembled off-site, was lowered into the containment chamber using precision gantry systems. The high-temperature gas-cooled reactors employed TRISO fuel particles encased in graphite, requiring specialized fuel handling and containment systems that were installed within the fuel building adjacent to the reactor vault. Above ground, mechanical and electrical auxiliaries were housed in turbine generator halls and heat exchanger enclosures. Power conversion was managed using helium-to-water heat exchangers that fed steam turbines, with the secondary loop connecting to both electrical generators and steam distribution systems used within the Dow chemical complex. To support redundancy and reliability, multiple trains of pumps, valves, and isolation systems were installed with segregated routing to prevent common cause failures. Electrical infrastructure included switchyards and medium voltage transformers tied into the local grid, as well as on-site power distribution to serve critical process loads. Instrumentation and control systems were centralized in a seismically isolated control building, equipped with safety-class digital control systems capable of autonomous reactor shutdown and passive cooling initiation. Fiber optic communication networks linked every module to this control hub for real-time data monitoring and diagnostics. Cooling systems relied on both mechanical draft cooling towers and auxiliary dry cooling radiators, designed to operate under varying ambient conditions while minimizing water withdrawal from nearby sources. Construction crews also installed extensive underground piping networks for the primary and secondary coolant loops, each pressure tested and radiographically inspected to meet nuclear-grade quality assurance standards. To ensure regulatory compliance, all phases of the project were conducted under a rigorous quality assurance framework, with continuous inspection and documentation in accordance with Nuclear Regulatory Commission requirements. Once systems were installed, integrated commissioning followed a phased approach, beginning with cold testing and followed by hot functional testing using non-nuclear heat sources. Only after successful completion of all operational verifications was fuel loading authorized. Upon activation, the SMR units began delivering reliable, carbon-free energy and industrial-grade steam, establishing the facility as a pioneering model for hybrid energy production in industrial settings.
The construction of One Vanderbilt, a super tall skyscraper located adjacent to Grand Central Terminal in Midtown Manhattan, involved a highly complex sequence of engineering, structural, and logistical operations. Rising to a height of over 1,000 feet, One Vanderbilt integrates advanced construction techniques and urban transit improvements into a single vertical development, setting a new benchmark for commercial office towers in densely built environments. The project demanded meticulous planning and coordination, particularly given its proximity to historic structures, active transit infrastructure, and high pedestrian traffic zones. Site preparation began with the demolition of several pre-existing mid-rise buildings. This process involved asbestos abatement, structural dismantling, and foundation removal. Due to the tight urban footprint and adjacent properties, much of the demolition was carried out using high-reach excavators and hydraulic breakers rather than traditional implosion or large-scale mechanical demolition. Once the site was cleared, excavation commenced for the new foundations, which reached over 60 feet below grade to accommodate the tower's deep basement levels and the integration of a new transit hall connecting to Grand Central Terminal. Subsurface conditions required the use of slurry wall construction to provide lateral earth support during excavation. A perimeter slurry wall, composed of reinforced concrete panels formed within bentonite-supported trenches, was installed to retain surrounding soils and water. Tiebacks and internal bracing were employed to ensure wall stability as excavation advanced. Excavated material was removed using conveyor belts and dump trucks, with loads scheduled during off-peak hours to minimize traffic disruption. The foundation system consisted of a combination of spread footings and deep caissons drilled into bedrock. The caissons, some exceeding 6 feet in diameter, were constructed using large rotary drilling rigs and reinforced with steel cages before being filled with high-strength concrete. These elements were designed to transfer the enormous vertical loads from the tower into the Manhattan schist below. A thick matte foundation slab was poured over the caissons, utilizing thousands of cubic yards of concrete delivered in a continuous 24-hour operation. The superstructure of One Vanderbilt utilized a composite structural system combining a reinforced concrete core with structural steel framing. The core, which houses elevators, stairs, and mechanical risers, was constructed first using slip-form technology. This technique involved the continuous pouring of concrete into a moving formwork system, allowing rapid vertical advancement. The core served as the backbone of the building, providing torsional resistance and lateral stability. Around the core, structural steel beams and columns were erected to form the building's floor framing. High-strength bolted and welded connections linked the steel elements, while metal decking and concrete topping slabs formed the composite floor systems. The building's tapering profile and multiple setbacks required specially fabricated steel members and custom connection details. Each steel floor was erected using tower cranes positioned within the core, later climbed to upper levels as the building rose. To achieve the building's slender profile and withstand wind loads, One Vanderbilt incorporated tuned mass damping systems at its upper levels. These systems consist of massive weights suspended and supported by hydraulic or spring systems, which counteract building sway during high wind events. The structural engineers also designed a system of outrigger trusses and belt trusses that tied perimeter columns to the central core, distributing lateral forces more efficiently and enhancing overall rigidity. The curtain wall system featured unitized glass and aluminum panels that were pre-assembled and tested off-site for quality and performance. Each panel included insulated glazing units with solar control coatings, contributing to the building's energy efficiency. The panels were hoisted into place using monorail rigs and suction equipment mounted to floor slabs, with careful alignment to ensure thermal and air barrier continuity. Integrated ventilation louvers and operable windows provided occupant comfort and facilitated natural airflow. Mechanical systems for One Vanderbilt were designed for high performance and tenant flexibility. The building was served by multiple mechanical floors housing chillers, air handling units, and water pumps. The chilled water system used high-efficiency centrifugal chillers with variable frequency drives, connected to fan-powered terminal units distributed throughout tenant spaces. The vertical distribution of mechanical services was handled through stacked mechanical shafts integrated within the core. Electrical infrastructure included redundant feeders from the utility grid, emergency diesel generators, and automatic transfer switches to ensure uninterrupted service. Advanced building management systems controlled lighting, HVAC, and security systems with sensors deployed to monitor occupancy and optimize energy use. High-capacity risers for telecommunications, data, and security cabling were installed to accommodate diverse tenant requirements. Vertical transportation consisted of over 40 elevators divided into zoned banks, some of which utilized destination dispatch technology to minimize wait times and energy use. Express elevators connected lower floors to sky lobbies, while service elevators were designed with extra depth to handle large tenant equipment and furniture. At the base of the tower, a new transit concourse was constructed to improve access to Grand Central Terminal and the subway lines beneath it. This involved underpinning sections of the historic terminal structure and constructing new passages, escalators, and ticketing areas. Complex waterproofing systems, including bentonite mats and integral water stops, were installed to protect the subterranean spaces from groundwater intrusion. Public realm improvements included widened sidewalks, landscape plazas, and an open-air pedestrian corridor that created visual and physical connections to Grand Central Terminal. Paving, lighting, and street furniture were coordinated to enhance pedestrian circulation and safety.
With healthcare rapidly advancing, the expansion of the Mayo Clinic campus in Phoenix required a highly coordinated approach to medical facility construction on an active site. Rather than developing on a greenfield, this project had to integrate new structures, towers, treatment areas, surgical suites, and utility cores into a functioning hospital environment without disrupting ongoing clinical operations. One of the first construction challenges was establishing a secure and phased logistics plan. Construction zones were partitioned from patient access routes using temporary fencing, directional signage, and sound attenuating barriers. Materials and equipment deliveries were tightly scheduled during off-peak hours, and tower crane operations were restricted to specific times to avoid interference with medical helicopter flight paths. Early enabling work involved the relocation of existing utilities, including domestic water lines, oxygen and medical gas conduits, and high-voltage electrical feeders, all of which had to be rerouted through temporary above-ground bypasses to maintain uninterrupted service. Structural systems for the hospital towers used a cast-in-place concrete frame with post-tension slabs, enabling open interior spans suited to evolving clinical layouts. The concrete mix was carefully designed for rapid strength gain to maintain construction pace, with high early strength additives and thermal control measures to avoid cracking. Columns were formed with reusable modular formwork, while floor plates were poured in large sequences using pump trucks and placing booms. Seismic detailing was embedded into shear walls and core walls, given the region's moderate seismic classification and the facility's essential use designation. Mechanical, electrical, and plumbing systems were among the most intricate components of the expansion. A centralized mechanical plant was expanded with additional chillers, boilers, and air handling units, each set on isolated inertia bases to limit vibration transmission to clinical environments. Mechanical penthouses and interstitial floors allowed for horizontal distribution of large ductwork, steam, condensate return, and reverse osmosis water piping. Extensive MEP coordination was performed through clash detection using 3D BIM modeling, ensuring ceiling plenums remained serviceable while also complying with stringent infection control requirements. Medical gas systems were extended from new bulk storage tanks through stainless steel piping networks with orbital welded joints, each one subject to 100% radiographic inspection. Redundant power was supplied by new diesel generator banks, paralleled with existing infrastructure, and backed by automatic transfer switches and battery UPS systems located in dedicated electrical rooms. Isolation panels, surge protectors, and clean power transformers were also installed for sensitive imaging equipment. Interior construction was sequenced to align with medical equipment installation schedules. Lead-lined walls and shielded ceilings were placed in radiology and surgical rooms, while vibration-isolated slabs and RF shielding were installed in MRI suites. Finishes included seamless epoxy flooring, antimicrobial wall protection, and hospital-grade ceiling systems with integrated lighting and air diffusers. Infection control risk assessments governed every phase, with negative pressure containment zones, HEPA filtration, and daily clean protocols enforced throughout active areas. Exterior elements incorporated high-performance glazing, architectural precast panels, and metal screen walls to conceal rooftop equipment. Site work included new patient drop-offs, staff parking, and ambulance circulation paths, all coordinated with civil stormwater infrastructure and ADA-compliant design. Ultimately, the Mayo Clinic Phoenix expansion merged complex medical infrastructure with construction excellence to produce a world-class facility that continues to evolve in parallel with modern healthcare delivery.
The Port of Long Beach Middle Harbor Redevelopment Project is a large-scale maritime infrastructure initiative aimed at modernizing and consolidating two aging shipping terminals into a single, highly automated, and environmentally sustainable container terminal. Located within one of the busiest ports in the United States, the project enhances cargo handling capacity, operational efficiency, and environmental performance, positioning the Port of Long Beach as a global leader in port technology and green logistics. Spanning over 300 acres, the redevelopment required extensive dredging, land reclamation, structural upgrades, and the implementation of advanced terminal automation systems. The initial phase of the project involved the demolition of obsolete structures, including wharves, cranes, warehouse buildings, and paved storage yards. Asbestos abatement, utility disconnection, and hazardous materials removal were carried out before full demolition could proceed. Controlled demolition methods and water suppression systems were used to mitigate dust and environmental impact. Salvageable materials such as steel, concrete, and timber were sorted and recycled, aligning with the port's sustainability goals. Once the site was cleared, major marine construction began. The waterfront area underwent significant dredging to deepen the berths to accommodate post-Panamax and ultra-large container vessels. Dredging operations used hydraulic cutter suction and clamshell dredges, removing silt and sand to reach depths exceeding 50 feet. Dredged materials were transported to offshore disposal sites or used as fill for land reclamation elsewhere within the harbor. The berths were then reconstructed with reinforced concrete wharf structures supported by large-diameter cast-in steel shell piles driven deep into the subsurface sediments. Each wharf section was designed to support the next generation of ship-to-shore gantry cranes, requiring high-capacity pile caps and deck slabs with post-tensioned reinforcement. Fender systems, mooring bollards, and ship access ladders were installed along the quay wall, meeting international standards for vessel accommodation. The cranes themselves were mounted on embedded crane rails with power and data conduits integrated into the wharf edge, enabling fully electrified operation. Simultaneously, the terminal's backland area was regraded and compacted to create a uniform, high-strength surface for container storage, truck lanes, and support facilities. Paving was done using reinforced concrete designed for heavy axle loads. A network of subsurface utilities, including stormwater drains, electrical conduits, water mains, and fire protection loops, was installed below grade, coordinated through 3D modeling to avoid conflicts and streamline future maintenance. One of the hallmark features of the Middle Harbor redevelopment was the integration of automation technology into terminal operations. Automated stacking cranes, guided by a terminal operating system, were deployed in container yards. These cranes operate on fixed rails and are powered by electricity, dramatically reducing emissions and labor costs. Containers are moved between yard stacks and transfer zones, where manned or automated vehicles deliver them to and from ships or trucks. Positioning accuracy, collision avoidance, and task optimization are managed through centralized software, interfacing with container tracking systems and real-time data networks. The truck gate complex was also redesigned to support rapid processing and minimize idling. Optical character recognition, biometric verification, and license plate readers were installed to allow for automated identification and routing. RFID tags on containers and chassis enable seamless integration with the TOS, ensuring drivers are directed efficiently through the terminal. Queue management systems, electronic signage, and automated barriers improve safety and operational flow. The Middle Harbor Terminal was designed with an all-electric infrastructure to reduce its environmental footprint. This included electric cranes, yard tractors, and refrigerated container plug-ins powered by the terminal's shore-based electrical system. Ships docking at the terminal are provided with shore power connections, allowing them to shut down auxiliary engines and eliminate emissions while at berth. Substations and electrical vaults were strategically placed to distribute medium-voltage power throughout the terminal, while redundancy was built in to ensure uptime reliability. Stormwater management was another key environmental component. The redevelopment included construction of biofiltration basins, permeable paving in select areas, and underground detention systems to control runoff. These systems filter pollutants and reduce discharge volume into harbor waters. In addition, lighting systems were upgraded with LED fixtures and dark sky compliant shielding to minimize light pollution and energy consumption. Rail infrastructure was also upgraded to support near-dock intermodal capabilities. New tracks, switches, and crossovers were constructed to tie the terminal into the Alameda Corridor rail network, allowing for the direct transfer of containers between ships and trains without truck drayage. Rail-mounted gantry cranes service the on-dock rail yard, loading and unloading double-stack container trains efficiently while maintaining schedule flexibility. Construction was phased to allow portions of the terminal to come online, while other sections remained under development. Each phase included commissioning and testing of all systems, training of personnel, and calibration of automated equipment. Extensive coordination was maintained with the U.S. Coast Guard, Environmental Protection Agency, and local air quality districts to ensure compliance with safety and environmental regulations.
Initial groundwork for Phase 1 of the Texas LNG export terminal in Brownsville began with intensive marine and geotechnical surveys to assess the suitability of the shoreline for deepwater infrastructure. The construction site required extensive dredging operations to create a navigable ship channel and turning basin capable of accommodating LNG carriers. Cutter suction dredgers and hopper dredgers were deployed to remove millions of cubic yards of sediment, which were relocated to designated containment areas built with sheet pile enclosures and geotextile reinforcement. Onshore, the site was cleared and leveled using heavy earth-moving equipment, with special attention paid to creating stable embankments for heavy process equipment. Piling operations commenced early, with cast-in-place concrete piles driven deep into coastal clay strata to support both structural and mechanical loads. Foundation pads for the liquefaction trains, storage tanks, and auxiliary buildings were constructed using a combination of deep pile caps and heavily reinforced grade beams. The heart of the terminal, the liquefaction process units, were installed on elevated steel platforms designed to withstand hurricane-force winds and seismic events. Each train included gas pretreatment modules, cryogenic heat exchangers, and compressor skids that were prefabricated off-site and delivered via heavy haul transport. The refrigerant circuits used a combination of propane and mixed refrigerants, requiring precise installation of high alloy piping systems and high-capacity centrifugal compressors. Storage infrastructure featured full containment LNG tanks built with a pre-stressed concrete outer wall and a nickel alloy inner tank. These tanks were founded on deep mat slabs and included a suspended deck for boil-off gas handling equipment. Tank construction followed a sequential slip-forming technique for the concrete shell, while cryogenic insulation and inner tank welding were performed under tightly controlled environmental conditions. Loading infrastructure was built at the end of a new trestle-supported marine jetty. The jetty deck housed cryogenic piping, loading arms, vapor return lines, and safety systems, all supported by battered steel piles driven into the seafloor. The loading arms were installed with emergency release systems and swivel joints to accommodate tidal variation and vessel movement. Throughout the terminal, fire protection systems were deployed with high-volume deluge systems, gas detection arrays, and foam monitors at critical points. Instrumentation and control were integrated into a distributed control system housed within a blast-resistant operations center. By the end of Phase 1, the Texas LNG export terminal was equipped to handle its first liquefaction and loading operations, forming a cornerstone of US Gulf Coast LNG export capacity.
The LaGuardia Airport redevelopment project in New York City was an extensive modernization effort aimed at transforming one of the most outdated major airports in the United States into a state-of-the-art transportation hub. The redevelopment involved the complete demolition and reconstruction of Terminals B and C, the building of new roadways and taxiways, installation of modern baggage handling and screening systems, and the integration of advanced mechanical and electrical infrastructure, all executed while maintaining full airport operations. Spanning over 800 acres, the project required innovative construction techniques and phased implementation to address the logistical complexities of building in a fully operational airfield. Initial site preparation for the redevelopment began with extensive demolition work, including the removal of obsolete terminal structures, parking garages, and auxiliary buildings. This phase also involved extensive utility relocation, as critical services such as electrical power, natural gas, potable water, sewer lines, and telecommunications had to be rerouted to maintain service continuity. In addition, environmental remediation was carried out in accordance with regulatory standards, including soil testing and removal of any contaminated material. One of the most challenging engineering aspects of the project was the construction of the new Terminal B, while the old terminal remained operational. To achieve this, the new head house, which would serve as the central terminal building, was constructed in phases. A steel superstructure was erected on deep foundations comprised of driven piles reaching down to bedrock. The pile caps and grade beams formed a stable base for the vertical elements of the building. Structural steel framing was then installed, including long-span roof trusses to support the expansive check-in and baggage claim areas. The use of prefabricated components helped accelerate construction while reducing on-site labor intensity. A distinctive feature of the new terminal layout was the use of dual pedestrian bridges spanning active aircraft taxiways. These bridges connect the head house to two island concourses and are constructed of steel box girders and reinforced concrete decking. They were erected using balanced cantilever techniques with temporary supports and tensioning systems to maintain stability during installation. Each bridge was designed to maintain a clearance height sufficient for Group 3 aircraft to pass beneath, requiring precise survey and alignment coordination. Airside construction included the development of new aircraft aprons, gates, and taxi lanes. This required excavation and grading to achieve proper slope and drainage, followed by the installation of sub-base layers, geotextiles, and Portland cement concrete pavement. Aircraft-rated pavement thicknesses were designed based on expected load distribution from narrow-body and wide-body aircraft. Jet blast fences and visual guidance systems were integrated into the apron design to ensure safety during aircraft movement. On the land side, new roadways were constructed to streamline vehicular access to the terminals. These roads featured elevated and at-grade sections built using cast-in-place concrete and precast segments. Foundations for elevated roadways included drilled shafts and pile-supported abutments. Traffic was managed using temporary detours and signage, while new bridges and ramps were staged to avoid interfering with ongoing operations. Interior construction of the new terminals prioritized modularity and flexibility. Raised access floors allowed for the distribution of power and data cables, while mechanical systems were suspended in accessible ceiling plenums. HVAC systems used air handlers with variable air volume controls, connected to a central chiller plant for efficient cooling. Advanced fire suppression systems, including wet pipe sprinklers and clean agent suppression in sensitive areas, were coordinated through 3D modeling to avoid conflicts with structural and mechanical elements. The baggage handling system represented a critical logistical element, comprising miles of conveyor belts, automatic sorters, and explosive detection systems. These were installed in stages, with integration and testing conducted in tandem to ensure seamless operation. The entire system was monitored by a centralized control room equipped with diagnostic tools for system performance and fault detection. Electrical infrastructure included the installation of new substations, switchgear, and emergency backup generators. Redundancy was built into the power supply network to ensure uninterrupted service to terminal systems. Lighting throughout the terminal employed LED fixtures with daylight harvesting controls, while building management systems monitored energy consumption, air quality, and equipment status. Sustainability played a significant role in the design and construction process. The terminal buildings incorporated high-performance glazing, green roofs, and low-flow plumbing fixtures to reduce environmental impact. Stormwater management features included bioswales, underground detention basins, and oil water separators to treat runoff before discharge. The construction team adopted a design-build-delivery method to streamline coordination between contractors and designers, enabling faster decision-making and reducing change orders. Coordination was further enhanced through the use of building information modeling, which allowed multidisciplinary teams to resolve conflicts virtually before beginning physical work. Weekly progress reviews, safety audits, and schedule updates ensured that construction proceeded according to plan despite the dynamic nature of the airport environment.
From the outset, the Mac Innovation Park in Scottsdale presented a high-performance build scenario shaped by advanced logistics, rapid vertical development, and site-specific architectural programming. Situated within a high-demand commercial corridor, the project required precision scheduling and a phased construction approach to erect multiple speculative and build-to-suit structures tailored for high-tech manufacturing, office, and research uses. The first major activity involved grading and compaction over a multi-acre footprint. Scottsdale's desert soil conditions demanded moisture conditioning, followed by repeated passes of sheepsfoot and smooth drum rollers, monitored continuously with nuclear density testing to confirm subgrade integrity. Stormwater retention and drainage systems were integrated early, using a combination of underground retention vaults and surface bioswales lined with riprap to mitigate flash flood risks typical of monsoon seasons. Civil crews trenched for extensive underground utilities, embedding large diameter conduits and reinforced concrete storm drains well before foundations were poured. Structural systems across the park consisted primarily of tilt-up concrete panels, a method selected for its speed, cost efficiency, and thermal mass benefits in a desert climate. Once formwork was set on large slab beds, each wall panel was cast with embedded window bucks, utility sleeves, and conduit stubs. Steel reinforcement was tied with exacting placement to meet seismic and wind load criteria. After curing, these panels were lifted using high-capacity hydraulic cranes and braced temporarily with diagonal steel supports until the roof structure was completed. The concrete mix design included admixtures for shrinkage control and compressive strength exceeding 5,000 pounds per square inch to allow for early panel lifting without compromising durability. Roof structures utilized open web steel joists supported by steel girders and columns anchored to footings with precision-aligned base plates and epoxy grouted anchor bolts. Decking was installed using high shear connectors and puddle welds, then covered with insulation and a reflective TPO membrane for energy efficiency. HVAC systems were rooftop mounted and supported by custom-built steel dunnage frames to reduce structural penetration through the roof. Mechanical coordination involved extensive pre-planning through building information modeling to avoid clashes between ductwork, piping, and electrical raceways within tight ceiling plenum spaces. Interior build-outs were varied depending on the end user, but commonly involved raised access flooring, modular cleanroom compatible partitions, electrostatic discharge safe surfaces, and filtered ventilation systems for research or manufacturing spaces. Electrical infrastructure featured heavy capacity switchgear, isolated ground panels, and redundant feeds where mission-critical operations were anticipated. Fiber optic cabling and wireless mesh networks were embedded throughout to support high data throughput and low latency connectivity. The exterior envelope included architectural elements such as aluminum curtain walls, insulated metal panels, and sunshade louvers oriented according to solar exposure analysis. Landscaping featured xeriscape planting schemes with drip irrigation systems and shaded pedestrian pathways to enhance sustainability and user comfort. Site lighting was designed with cut-off optics and smart sensors to minimize light pollution while ensuring safety.
The construction of the Intel semiconductor fabrication plant in Arizona, part of a multi-billion-dollar investment in domestic chip production, is a highly advanced industrial project that combines precision engineering, extreme cleanliness requirements, and massive mechanical and electrical infrastructure. Situated at Intel's existing Ocotillo campus in Chandler, this expansion adds new fabs to one of the most technologically sophisticated manufacturing sites in the world. The project supports Intel's strategy to enhance U.S. semiconductor capacity and resilience in the global supply chain, and involves the creation of highly specialized cleanroom space, support buildings, and utility systems capable of sustaining the rigorous demands of advanced chip fabrication. Site development began with large-scale excavation and grading to accommodate multiple large-footprint buildings, including cleanroom facilities, utility plants, and administrative structures. Subsurface conditions in the desert environment required over-excavation and replacement with engineered fill to achieve the uniform settlement and load-bearing capacity needed for precision manufacturing operations. Thousands of deep foundation elements, including auger cast piles and drilled piers, were installed beneath the fab buildings to isolate them from vibration and thermal expansion, both of which can interfere with nanometer-scale semiconductor production. Above the foundation level, a reinforced concrete mat slab was poured to provide a base for the fab. This slab required an extremely flat and level surface finish, with tolerances far exceeding those used in conventional construction. Specialized concrete mixes were used to control shrinkage and thermal cracking, with continuous placement operations and finishing conducted under tightly controlled environmental conditions. The superstructure of the semiconductor fab buildings was constructed using a combination of steel framing and reinforced concrete walls, designed to support the heavy mechanical loads and provide a rigid frame for the cleanroom environment. The cleanroom floors were constructed using raised access systems, which allow for the routing of process utilities, electrical conduits, and airflow distribution beneath the floor surface. These systems are supported by structural steel decks designed to limit deflection and vibration to imperceptible levels. One of the most complex aspects of the Intel fab construction is the integration of its process support infrastructure. Semiconductor manufacturing requires ultra-pure gases, deionized water, high-voltage electrical power, vacuum systems, and chemical waste handling, all of which must be delivered and maintained with absolute precision. Gigantic central utility buildings were constructed adjacent to the fab to house air compressors, chillers, scrubbers, water treatment systems, and gas cabinets. These systems feed into the fab through an intricate network of insulated stainless steel piping, double-walled chemical lines, and redundant electrical feeders, all routed through dedicated utility corridors and mechanical chases. HVAC systems for the fab are designed to maintain cleanroom conditions in accordance with ISO Class 1 to Class 5 standards, depending on the process zone. These systems involve massive air handling units that filter air through high-efficiency particulate air and ultra-low penetration air filters, delivering laminar airflow through the cleanroom ceiling. Air change rates are among the highest of any building type, and temperature, humidity, and particulate levels are continuously monitored and adjusted by automated building management systems. The cleanrooms themselves are modular in construction, with prefabricated panels used to form walls, ceilings, and integrated air plenums. Interior finishes are composed of non-shedding, electrostatically dissipative materials that resist chemical corrosion and minimize contamination risk. Workers must pass through multi-stage gowning areas, air showers, and decontamination chambers before entering these spaces, and construction crews must follow similar protocols during the fit-out phase. Electrical infrastructure is equally critical, as semiconductor fabs consume vast amounts of power with a need for extremely reliable delivery. On-site substations, switchgear, uninterruptible power supplies, and emergency generators are installed in layered configurations to support continuous operation. Power quality is managed through real-time monitoring and conditioning systems to prevent voltage fluctuations or outages that could compromise sensitive fabrication tools. Process tool installation represents a major component of fab construction. These tools, which include photolithography scanners, etchers, ion implanters, and chemical vapor deposition chambers, are extremely sensitive and must be installed on vibration-isolated foundations with precise alignment. Tool hookup involves hundreds of connections for process gases, liquids, vacuum, and data communications. Each tool is commissioned individually and tested extensively before being certified for production. To manage water use, the site features a cutting-edge water reclamation plant that recycles process water for reuse in cooling towers and rinse processes. This system is critical in Arizona's arid climate and is one of the most advanced water sustainability efforts in industrial manufacturing. Waste treatment systems also neutralize and separate chemical byproducts for proper disposal, in compliance with federal and state environmental regulations. Construction was carried out using lean methodologies and building information modeling, enabling real-time coordination between trades and minimizing clashes between complex mechanical systems. Prefabrication was employed extensively for piping racks, electrical skids, and modular wall panels to accelerate installation and reduce site congestion. With thousands of workers on site daily, logistics were managed using zone scheduling, digital tracking, and real-time communication tools to maintain progress and safety.
Across the sprawling DFW Metroplex, the emergence of hyperscale data centers began with extensive land acquisition in strategically positioned industrial parks and technology zones. These parcels were selected based on proximity to high-capacity electrical substations, dark fiber routes, and minimal exposure to flood hazards. Before vertical construction could begin, civil engineers undertook large-scale earthworks to level the terrain, compact subgrade, and construct internal roadways capable of supporting the constant delivery of construction materials, generators, and prefabricated equipment modules. With the footprint of each data center sometimes exceeding several 100,000 square feet, foundations were designed for heavy point loads, particularly under mechanical galleries and electrical rooms. Reinforced concrete mats were poured atop dense layers of engineered fill and often included embedded anchor systems for equipment skids and heavy racks. Structural steel frameworks rose rapidly using pre-assembled columns and girders, lifted by crawler cranes and joined using high-strength bolted connections. Tilt-up concrete wall panels were commonly used for perimeter enclosure, offering both speed of erection and excellent thermal and blast resistance. Roof systems were engineered with significant load allowances to accommodate air handling units and dry coolers. Steel bar joists spanned long bays, supporting a composite steel deck that received a rigid insulation layer and a fully adhered membrane roofing system. Each penetration point was pre-coordinated with mechanical, electrical, and plumbing disciplines to avoid interference and maintain weather-tight integrity. Electrical systems formed the backbone of hyperscale operations, beginning with dual utility feeds backed by on-site substations built specifically to meet the center's megawatt-scale demands. Power was stepped down through gas-insulated switchgear before being distributed via bus duct and armored cable to critical electrical rooms. Redundant, uninterruptible power supply units were housed in independent, fire-rated enclosures, with each feed isolated to maintain Tier 4 design principles. Diesel backup generators, often rated between 2 and 3 megawatts each, were installed on exterior pads with bulk fuel storage and automated day tanks. These were integrated into a site-wide power management system that allowed seamless transition during utility outages. Power distribution units and remote power panels fed rows of server racks with branch circuit monitoring for granular load balancing. Cooling infrastructure was designed for energy efficiency and fault tolerance. Indirect evaporative cooling systems, chilled water loops with centrifugal chillers, and direct expansion systems were all used depending on the operator's design preference. Cooling distribution was delivered through underfloor plenums or overhead ductwork, coordinated with containment systems that separated hot and cold aisles. CRAC, and CRAH units operated in N+1 or 2 N configurations, and thermal storage tanks were added in some locations to buffer peak load conditions. Inside the white space, raised flooring was laid over pedestals anchored to the slab, allowing for airflow and cable management. Overhead trays carried fiber optic trunks, copper power conductors, and sensor cabling. Fire protection was achieved through clean agent suppression systems and pre-action sprinklers, triggered by multi-sensor detection arrays. To ensure long-term operational resilience, the commissioning process was exhaustive, including integrated systems testing and load bank simulations. As each hyperscale data center in the DFW Metroplex came online, it represented the convergence of massive power infrastructure, advanced thermal engineering, and mission-critical reliability built to serve the digital economy at scale.
The construction of the East Side Access Project in New York City is one of the most complex and technically challenging transit undertakings in the history of the United States. Designed to connect the Long Island Railroad to a new terminal beneath Grand Central Terminal in Manhattan, this massive infrastructure project required the excavation of multiple tunnel systems, the construction of subterranean caverns, and the integration of entirely new rail systems within one of the most densely built environments in the world. Spanning decades of planning and construction, the project unfolded deep beneath the city's surface, demanding extraordinary precision and coordination across multiple engineering disciplines. At the core of the East Side Access Project was the tunneling phase, which involved the excavation of nearly 15 miles of new tunnels beneath Queens and Manhattan. This began with the deployment of tunnel boring machines, each weighing hundreds of tons and extending over 400 feet in length. These machines were launched from access points in Queens and advanced westward under the East River through soft ground and bedrock. To maintain stability in varying geological conditions, different TBM technologies were employed, including earth pressure balance and slurry shield methods. The TBM simultaneously excavated and installed precast concrete segmental liners, forming a continuous circular tunnel as they progressed. Each tunnel required continuous monitoring of ground movement, with real-time data collected from instruments embedded in the surrounding soil and rock. Ground stabilization techniques such as ground freezing and jet grouting were employed where necessary to prevent subsidence and protect adjacent infrastructure. Spoil material from the excavation was transported via conveyor belts and muck trains to designated removal sites, where it was processed and disposed of according to environmental regulations. Once the primary tunnels were completed, work shifted to the construction of the Manhattan Caverns, which would house the new terminal platforms and tracks. Located approximately 100 feet below street level, these caverns were excavated using the controlled drill and blast method. Each blast was carefully calculated to fracture rock without damaging existing subway lines and utilities above. The excavated spaces were then stabilized using rock bolts, shotcrete, and steel ribs, followed by waterproofing membranes and reinforced concrete linings. The new terminal complex beneath Grand Central was designed as a bi-level structure featuring 4 platforms and 8 tracks. The layout included numerous cross passages, ventilation shafts, and emergency egress corridors. Each level was constructed with reinforced concrete floor slabs supported by massive girders and columns, engineered to distribute loads uniformly across the cavern walls and foundations. Structural steel framing was used extensively in mezzanine and concourse areas to allow for open spaces and flexibility in architectural finishes. A major component of the East Side Access Project was the installation of a complex track and signal system. This involved laying continuously welded rail on concrete ties set in ballastless track beds, designed for durability and low maintenance. The track alignment required precision to meet curvature and grade requirements, particularly as the trains transitioned from tunnel approaches into the terminal. Overhead catenary systems were replaced by a third rail electrification system compatible with Long Island Railroad rolling stock, necessitating the integration of new power substations and switching equipment. Advanced signal and train control systems were installed, including communications-based train control to enhance capacity and safety. These systems required extensive cabling, signal houses, and testing to ensure interoperability with the existing rail network. Fiber optic communication networks were also laid throughout the tunnels and terminal areas to support operational control and real-time monitoring. Vertical transportation was another critical aspect, given the significant depth of the terminal. High-capacity escalators, some extending over 90 feet in length, were installed to move passengers efficiently between the mezzanine and platform levels. Additionally, multiple banks of high-speed elevators were constructed to provide accessibility and redundancy. Mechanical rooms housing air handling units, chillers, and backup power systems were strategically located throughout the terminal to support passenger comfort and operational resilience. In Queens, the Harold Interlocking, one of the busiest rail junctions in the country, had to be completely reconfigured to accommodate new track alignments for East Side access. This required the installation of new flyovers, viaducts, and switches, while maintaining uninterrupted train service for Amtrak and the Long Island Railroad. Work in this area was conducted in multiple phases, involving track outages scheduled years in advance and executed with military precision. New signal towers and interlockings were built to streamline train movements and improve operational flexibility.
Unlike traditional airport projects built in undeveloped areas, the Mesa Gateway Airport expansion required surgical precision to retrofit and expand critical infrastructure within an operational airfield. The effort spanned terminal growth, airside improvements, and upgrades to utilities, all orchestrated under strict Federal Aviation Administration compliance and continuous coordination with airport operations. Initial groundwork focused on expanding the commercial terminal. This involved selective demolition of existing structures and pavement, followed by deep trenching to relocate utility lines such as jet fuel piping, communications fiber, and storm drains. Excavation was staged to avoid conflicts with active taxiways and required trench shielding, dewatering pumps, and utility phasing plans that prevented disruption to existing airport services. Potholing and ground-penetrating radar scans were performed to identify undocumented legacy utilities from the site's previous military use. Terminal expansion required a structural system that combined steel moment frames with composite decking, supported by drilled piers tied into deep foundation beams. The steel frame was erected using high-reach cranes that were coordinated with the airport's control tower to avoid airspace intrusion, particularly during girder lifts near the active apron. Roof decking was fireproofed with sprayed-applied materials, and roof insulation assemblies were capped with a single-ply membrane roofing system designed to withstand high desert UV exposure and monsoonal winds. Passenger processing areas were built with forward-looking flexibility. Baggage handling systems were laid out beneath the slab-on-grade level, supported by trench drains and conveyor pits formed with cast-in-place concrete. Conveyor belts, diverters, and scanners were pre-assembled off-site and installed as modules to reduce installation time within a compressed schedule. Check-in counters, TSA security lanes, and automated boarding gate systems were backed by robust data infrastructure routed through overhead cable trays, linked to secure IT closets, and network hubs located in protected zones behind the scenes. Airside improvements extended to taxiway extensions and apron reconfiguration. Crews used slip-form paving machines to place Portland cement concrete with dowel joints, constructed in multi-lane widths with tight alignment controls. Concrete batch plant operations had to meet FAA quality standards for airfield pavements, including flexural strength and surface smoothness. New lighting systems, edge lights, taxiway center lines, and approach indicators were installed within pavement cans fed by underground duct banks, all tied into the airport's airfield lighting control system. Jet bridges were added and coordinated with apron regrading to match aircraft door sill heights. Reinforced apron paving with fuel hydrant pits, ground power units, and potable water hookups were integrated at each new gate position, enabling faster turnaround times for commercial airliners. Drainage for apron areas was routed to oil water separators to maintain environmental compliance before entering the municipal storm system. To support future growth, a new central energy plant was constructed, housing chillers, boilers, backup generators, and water softening systems. Mechanical systems were routed through underground utility corridors leading to terminal mechanical rooms equipped with air handlers, VAV boxes, and HEPA filtration. All critical systems were designed with N+1 redundancy to ensure uninterrupted operation.
The Springfield Rail Improvements Project is a comprehensive transportation infrastructure initiative designed to enhance rail operations, vehicular traffic flow, and safety within the city of Springfield, Illinois. Located along the primary north-south corridor for freight and passenger rail in central Illinois, this project addresses long-standing issues related to at-grade crossings, traffic delays, emergency vehicle access, and community connectivity. It involves the realignment of rail lines, construction of new underpasses and overpasses, installation of modern signaling systems, and the development of consolidated corridors to better manage the coexistence of rail in urban environments. The core of the project is the consolidation of multiple existing rail corridors onto a single, upgraded alignment along the 10th Street corridor, which will serve as the main north-south route for both freight and Amtrak passenger trains. This realignment requires the relocation of tracks previously running along the 3rd Street corridor. As part of this shift, new double-track sections are constructed using continuously welded rail on concrete ties supported by engineered ballast and subballast layers. Subgrade preparation involved excavation to remove unstable soil, replacement with select fill, and compaction to achieve the necessary bearing capacity and drainage properties. The new corridor includes improvements to the track profile, geometry, and elevation to ensure compliance with modern rail standards. Geometric design ensures proper curve radii, super elevation, and grade transitions, accommodating both high-speed passenger operations and heavy freight trains. Drainage systems, including French drains, culverts, and swales, are installed along the right-of-way to protect the track structure and minimize water infiltration. Grade separation is one of the project's defining features. Multiple new underpasses and overpasses are constructed to eliminate at-grade crossings, enhancing both safety and efficiency. These structures include roadway underpasses with retaining walls, bridge decks, and approach embankments. For underpasses, construction begins with temporary traffic rerouting, followed by excavation and the installation of shoring systems such as sheet piling or soldier pile and lagging walls. Reinforced concrete box culverts or beam and slab bridge decks are installed to carry rail lines over the depressed roadways. Bridge abutments are supported by deep foundations, typically drilled shafts or driven piles, depending on subsurface conditions. Concrete formwork, reinforcement, and pour sequencing are closely coordinated to maintain quality control and structural integrity. Stormwater detention basins and pump stations are added near underpasses to manage runoff and prevent flooding during storm events. Signal and communications infrastructure throughout the corridor is upgraded to include positive train control, wayside signals, automatic block signals, and grade crossing protection where crossings remain. Fiber optic cables are laid in conduits adjacent to the track structure, forming the backbone of the communication system. Signal houses are prefabricated and equipped with relay logic, batteries, and interface panels, enabling centralized traffic control and real-time monitoring of train movements. To minimize disruption during construction, much of the work is staged. Temporary shoe fly tracks are built to divert rail traffic around active work zones. These detour tracks are constructed to full structural standards and include turnout switches, ballast, and signal integration to maintain continuity of operations. As permanent infrastructure is completed, trains are shifted onto the new alignment, allowing for the removal of old track and crossings. Environmental considerations are integrated into every phase of the project. Wetlands, drainageways, and wildlife habitats are assessed during design, with mitigation strategies implemented where impacts are unavoidable. Erosion control measures such as silt fencing, seeded slopes, and temporary sediment basins are deployed during earthwork operations. Noise and vibration studies are conducted, leading to the installation of sound walls and the use of ballast mats or resilient rail fasteners near sensitive receptors like residential neighborhoods or historic districts. Public engagement is also a central component, with ongoing coordination between city officials, the Illinois Department of Transportation, and the Federal Railroad Administration. Stakeholder meetings, community briefings, and property owner consultations ensure transparency and allow concerns about property access, construction impacts, and aesthetics to be addressed proactively. In many locations, enhancements to urban design are incorporated into the project, including landscaping, pedestrian pathways, lighting, and public art installations that reflect Springfield's cultural identity. The Springfield Rail Improvements Project also supports broader goals of regional transportation planning. By consolidating rail operations onto a dedicated corridor, the project lays the groundwork for expanded passenger rail service, including future high-speed rail connections along the Chicago to St. Louis corridor. It also facilitates improved freight logistics by reducing delays caused by vehicle rail conflicts and allowing for higher throughput along a modernized rail line. Construction logistics are tightly managed, with detailed scheduling, traffic control plans, and safety protocols. Equipment staging areas, material stockpiles, and worker access routes are established to reduce interference with local traffic and maintain construction productivity. Work progresses in multiple segments simultaneously, leveraging different contractors and crews to meet project milestones while keeping disruption to the community at a minimum.
Starting with site selection for the Gigapop data center in Red Oak, engineers prioritized proximity to major fiber routes, low seismic risk, and stable ground conditions. Once the parcel was secured, initial development began with topographic surveys and soil borings to evaluate bearing capacity and groundwater levels. Given the data center's critical function, achieving a stable substructure was imperative. Contractors excavated to a depth of several feet, removing organic material and replacing it with engineered fill compacted in lifts. Deep foundation systems, such as drilled piers, were deployed in zones with variable soil strata to ensure long-term structural stability. The facility's footprint was laid out to accommodate modular expansion with a steel-reinforced concrete slab on grade serving as the foundation platform. Reinforcing steel cages were assembled on site and tied into slab pours, using continuous rebar loops to enhance crack resistance and load distribution. After curing, the slab served as the base for pre-engineered structural steel framing. Steel columns and wide flange beams were anchored into embedded base plates and erected using cranes, with lateral bracing and cross members installed to provide rigidity against wind and seismic loads. Envelope construction followed with the installation of insulated metal panels for both thermal performance and security. The roofing system used a mechanically fastened thermoplastic polyolefin membrane over tapered insulation to achieve proper drainage. Roof curbs were pre-installed to support future mechanical units, while penetration points for cabling and ductwork were carefully sealed to maintain the building's energy envelope and meet FM global standards. Critical to the facility's design was its mechanical and electrical infrastructure. Redundant power delivery was achieved using dual utility feeds connected to independent switchgear systems. Below-grade duct banks housed medium voltage cables leading to unit substations, which stepped down voltage for distribution within the facility. Emergency power was backed by multiple diesel generators set on reinforced concrete pads, connected to automatic transfer switches and uninterruptible power supply systems. Each UPS module was installed within a conditioned electrical room, outfitted with fire-rated walls and clean agent fire suppression systems. Cooling was accomplished using a chilled water system with air-cooled chillers mounted on structural steel platforms outside the main building. Inside, computer room air handlers circulated chilled air through raised floor plenums, delivering conditioned air directly to server aisles. Hot aisle containment was implemented to isolate and return warm exhaust air, maximizing cooling efficiency and minimizing energy usage. Cooling system piping was routed through a looped configuration with isolation valves to allow maintenance without service interruption. The data hall itself featured anti-static raised flooring, overhead cable trays for power and fiber distribution, and seismic-rated server racks bolted to the slab. Environmental monitoring systems were installed to track temperature, humidity, and particulate levels, all integrated into a building management system with real-time alerts. Security was another major focus, involving perimeter fencing, man-trap entry vestibules, biometric access control, and 24/7 surveillance. All systems were tested through integrated commissioning protocols to validate performance under simulated failure conditions. Once validated, the Gigapop data center in Red Oak went live, offering high availability colocation and cloud services in a purpose-built, mission-critical facility engineered for scalability and resilience.
The redevelopment of Penn Station in New York City is a large-scale infrastructure and architectural initiative designed to transform one of the most heavily trafficked and functionally outdated transportation hubs in the United States into a modern, efficient, and passenger-focused facility. This multifaceted project involves the complete overhaul of existing station elements, integration of new transit connections, and the construction of Moynihan Train Hall as an extension of Penn Station's operational footprint. The redevelopment process unfolded across multiple phases, each requiring intense coordination between civil, structural, mechanical, and transportation engineering disciplines, all while maintaining continuous transit service for hundreds of thousands of daily commuters. The first critical step in the redevelopment was the structural conversion of the James A. Farley Post Office building into the new Moynihan Train Hall. This Beaux-Arts structure, located directly west of Penn Station, was originally constructed with massive granite walls and steel floor framing. Adapting this historic facility to serve as a modern rail terminal required surgical demolition of interior structural elements and the reinforcement of floor slabs and columns to accommodate new loading requirements. The most dramatic transformation occurred with the installation of a vaulted steel and glass skylight system over the former mail sorting room, now repurposed as the main concourse. This skylight was supported by new structural steel arches tied into the existing steel framing through moment-resisting connections. The entire installation had to be designed to accommodate differential settlement, thermal expansion, and seismic movement. Beneath the concourse, platforms and tracks serving Amtrak and Long Island Railroad were upgraded to meet modern standards. This involved improving vertical circulation with new escalators and elevators, reinforcing platform edges, upgrading lighting, signage, and wayfinding systems, and integrating accessibility features in compliance with the Americans with Disabilities Act. The mechanical ventilation systems serving the platforms were also expanded, including the installation of new fans, air shafts, and smoke evacuation ducts. The expansion of concourse areas continued under the streets and buildings adjacent to the existing Penn Station, where new subterranean pedestrian corridors were excavated using a combination of cut and cover and hand mining techniques. These corridors were lined with waterproof concrete and outfitted with finishes that matched the aesthetic of the new train hall. Special care was taken during excavation to protect nearby building foundations and subway infrastructure, employing instrumentation to monitor ground movement in real time. Within the original Penn Station footprint, structural retrofits were carried out to open up the low-ceilinged areas that had long hindered passenger flow and visibility. This included the removal of non-structural mezzanines and drop ceilings, the relocation of HVAC ductwork, and the replacement of outdated mechanical systems. Load-bearing columns were clad with fire-rated materials, and floors were refinished with terrazzo and stone tile to improve durability and appearance. Lighting systems were upgraded to high-efficiency LED arrays, integrated with motion sensors and daylight harvesting controls. A new entrance pavilion was constructed on 7th Avenue, creating a prominent street-level presence for the station. The pavilion consisted of a steel-framed structure with a glass facade supported by tensioned cable trusses. This open and transparent design brought natural light into the concourse and served as a visual counterpoint to the previously closed-off street frontage. Beneath the entrance, new circulation stairs, escalators, and elevators were installed to move passengers from street level to concourse and platform levels with minimal congestion. Mechanical, electrical, and plumbing systems throughout the redeveloped station were completely overhauled. Central utility plants were upgraded with high-efficiency chillers, boilers, and air handling units. These systems were connected to a distributed network of variable air volume boxes and demand-controlled ventilation points designed to adapt to occupancy loads in real time. Electrical distribution was modernized with new substations, transformers, and switchgear capable of supporting expanded digital signage, surveillance systems, and tenant loads. All systems were tied into a centralized building management system with touchscreen controls, alarms, and energy monitoring capabilities. The redevelopment also emphasized sustainability, with features such as green roofing, stormwater management systems, and low-impact construction materials. Green roofs were installed atop portions of the Moynihan Train Hall and the new entrance pavilion, supported by reinforced roof slabs and integrated drainage systems. Stormwater runoff was directed to underground detention tanks and treated before being discharged or reused for non-potable applications such as irrigation. During the course of construction, maintaining uninterrupted train service remained a top priority. Work was scheduled in off-peak hours and overnight shifts to limit disruptions. Temporary barriers, rerouted access paths, and detailed construction phasing plans allowed contractors to isolate active work zones from public areas. Safety was ensured through real-time coordination with Amtrak, Long Island Railroad, and New Jersey Transit, with flagging crews and communication protocols in place for track-level activities. Coordination with existing infrastructure was another critical component of the project. Penn Station interfaces with subway lines, path trains, and multiple street-level transportation systems. The redevelopment included improvements to subway entrances, ticketing areas, and passageways connecting the transit systems. Structural ties were established between the old and new facilities with seismic joints and expansion joints incorporated to account for differential movement between the structures.
Not every freeway expansion challenges engineers with such extreme topographic variation as the Interstate 17 Black Canyon Freeway widening. This project, traversing from North Phoenix up through mountainous terrain toward Flagstaff, required overcoming both urban congestion constraints and rural geological complexities. It was not a uniform widening effort. Rather, it entailed a hybrid approach of adding general-purpose lanes, climbing lanes for freight vehicles, and in some segments, reversible flex lanes designed to accommodate peak traffic flow. Construction sequencing began with extensive earthwork, particularly through the northern sections where cuts into basaltic rock were necessary. Controlled blasting operations were scheduled in tightly regulated windows to reduce traffic disruption and environmental impact. Each blast zone underwent pre- and post-blast surveys to ensure rock stability and confirm that the blast radius remained within safety thresholds. Debris was excavated using high-reach excavators and loaded into articulated dump trucks for repurposing as fill in adjacent embankment zones. These embankments were constructed in compacted lifts, each tested for moisture content and density to meet strict compaction standards necessary for load-bearing capacity. In the more urbanized southern corridor, work was performed in narrow medians and shoulders. Traffic staging required temporary barrier placement, restripping, and real-time signal adjustments to maintain throughput while isolating work zones. Construction of new lanes meant full-depth pavement installation, beginning with subgrade preparation, placement of aggregate-based course, and then successive lifts of asphaltic concrete. The mix design was tailored for durability in high-temperature conditions, incorporating polymer-modified binders and performance-graded asphalt to resist rutting and thermal cracking. Bridges posed a significant element of the widening effort. Many existing structures over washers and arterial roads were widened symmetrically using cast-in-place concrete decks over precast, pre-stressed concrete girders. Abutments and piers were reinforced with drilled shaft foundations, extending deep into competent bedrock to mitigate differential settlement. Expansion joints, bearing pads, and shear keys were detailed to accommodate seismic and thermal movements while maintaining deck continuity. Stormwater management infrastructure was upgraded in tandem, involving the installation of reinforced concrete box culverts and oversized pipes beneath the widened footprint. In some areas, detention basins were excavated with engineered outlet structures to manage discharge rates and protect downstream properties from flooding. Erosion control measures, including soil binders, riprap armoring, and hydro-seeding, were deployed along slopes and drainage channels as permanent stabilization. Intelligent transportation systems were embedded throughout the corridor. This included dynamic message signs, closed-circuit TV cameras, radar-based traffic sensors, and fiber optic communication backbones. These systems were linked to the Regional Traffic Operations Center, enabling real-time monitoring and adaptive traffic management, particularly useful for managing incidents and peak period congestion. Guardrail systems, median barriers, and high-visibility signage were installed during the final phase. Road striping used thermoplastic materials with reflective beads for enhanced night visibility. Before opening, each section underwent load testing, profile evaluation, and friction testing to ensure geometric and safety compliance.